Good morning, everyone, and thanks for being here for the AI4Media workshop on human and society-centered AI. We have quite a lot of interesting topics today, so we'll discuss, we'll have presentations from project partners about detection of deepfakes in multimedia content, about the dynamics of social media conversation, about the automatic in-depth analysis of political discourse, about the fusion of different signals to characterize users' behavior, about the human-centered analysis of news consumption, and also about real effect of data sharing. We have also two very interesting invited presentations from external speakers. So the first one is Elena Koshkina from Queen Mary University, who will discuss state of the art of automatic rumor verification methods. And we also have Juan Agoga from the French National Center for Scientific Research, who will speak about the detection of political ads which are served on social media. So this gives us quite broad spectrum of topics related to AI and society, and also the human side. And what we want to do in this with this works is to contribute to a healthier political public debate with particular focus on politics, which is very, very important. Without further ado, I will invite Akis Papadopoulos to give us a presentation about deepfake detection. So an overview of this topic. And okay.
Hello, I hope you can see me.
Yes.
Hear me. Good morning. Thanks for having me here today. I will going to give a brief overview of the area of deepfake detection. It's a very well known and popular research area nowadays, and we have been working on it for almost a couple of years now. My colleagues Chronis Chartidis and George Kordopatis are at the front of this work. Let's start. I guess most of you, if not all, have come up with the term deepfakes and probably already know a bit or a lot about it. Generally, deepfakes refer to content that at least partly has been generated by deep neural networks and seems authentic to the human eye. It started a few years ago from a particular model called deepfakes, hence the name. But nowadays, it refers to a much broader category of synthetic content. And the common element is the use of deep neural networks. But it can refer to many different architectures and also additional techniques. Most commonly and most seen in practice are synthetic media that also include face. And there are, broadly speaking, four main types of face-focused deepfakes. Entire face synthesis. So starting from some random vector, we generate a face from scratch. And attribute manipulation or attribute editing, where essentially we can add glasses to a person or change the hair. And the third category is identity or face swap or replacement, which is also a very popular type of deepfakes. And last but not least, expression swap or face reenactment, which also includes lip syncing and trying to make a person speak something that they didn't. The domain has seen explosive popularity over the last years, as these two figures show. On the left-hand side, we see the number of papers mentioning the term GANs, which stands for Generative Adversarial Networks, and was first introduced in 2014. And on the right-hand side, from a recent survey, we've seen again the exponential growth of papers containing the term deepfakes in their text. In addition to the large academic interest, we have seen also remarkable improvements in terms of the quality. Here, this was from a tweet by Ian Goodfellow, the inventor of the generative adversarial networks, and shows how quickly the quality has improved over the last 5 years. Actually, this stops in 2018, so you can imagine that things today are much more convincing and high quality. And to attest this, this year, in the beginning of the year, we had this deepfake featuring Tom Cruise circulating on TikTok and quickly shared on other social media platforms. This turned out to be a deepfake created by a video effects specialist, Chris Hume, and it was not possible to detect it by any of the commercial deepfake detection services. And it was not also discernible by human inspection, even by experts. So there was a lot of discussion because this level of realism was deemed as really risky, and many people found that there was big potential for misuse. However, the video effects specialist himself told that it was not created automatically. There was a lot of manual editing involved, a lot of expertise, skill, and time, and even an impersonator. So we are still not at the level, at such a level that automatic methods can create so convincing deepfakes. The most common elements in today's deepfake generation systems are the very well-known encoder-decoder architectures, the vanilla generative adversarial networks, and several popular extensions, cycle-GAN, pix-to-pix, recursive neural networks, and more recently, also transformer architectures. There is a very nice overview of these generation architectures by Mirsky and Lee, which I highly recommend. The domain in general is evolving very fast, and new architectures and new improvements appear by the day. In addition to the core generation architecture, there is also a whole pipeline, including pre-processing and post-processing operations with more, let's say, conventional computer vision and image processing techniques, and with a varying level of sophistication. And this can be implemented either by some open source tools like FaceSwap and Deep Face Lab, or by some custom tools, or even by more conventional video and image editing tools like Adobe Premiere. As we speak, in this year, it is still possible to detect by manual inspection a good number of deepfakes on the internet, since they are still suffering from some imperfections. And there is a very interesting articles by Associated Press which points to the areas in the face, around the eyes and the lips, around the earlobes, where even by human inspection we can identify some artifacts like blurry areas or fuzzy areas or inconsistencies, and this can help us identify a deepfake on the internet. However, as you've seen before, the technology is improving a lot, and we cannot expect that human inspection will be sufficient in the years to come. And for that reason, there is a very large variety of deepfake detection approaches, and by studying a number of them, we can broadly classify them in these 4 categories. There are more categories, of course, and we can do a more fine-grained categorization. So this is by no means comprehensive, but it can give an indication of the types of methods that are used. So the first category tries to extract physiological signals or biometric signals from the persons shown in a video. And these include, for instance, blinking frequency or the corneal specular highlights and their symmetry, or the pulse of a person by photoplethysmography methods, and so on and so forth. A second category of methods is the so-called artifact-based detection, which essentially try to emulate a very good human inspector who tries to identify artifacts like the ones I showed in the previous slide, like limited resolution, blurring, local artifacts around points of interest in the face. A third category is the, let's say, traditional convolutional neural network-based approaches, which employ at their core a backbone network like MesoNet, ExceptionNet, EfficientNet, capsule networks, and of course they also expand using some tricks. And last but not least, there are also methods that operate on the frequency domain and try to identify special patterns there. Also, there is another unique category of methods, and I think it's going to be also presented later today by our colleagues at University of Florence, that is making use of the temporal information, so the sequence of frames in a video. And this also seems to be an emerging category of methods. A very important aspect of deepfake research is the availability of datasets. A few years ago, there had been only a few and very limited in size datasets. But lately, we've seen also big tech companies enter into the game, and they have released some very valuable resources for the community. The latest popular and big dataset is the Deepfake Detection Challenge dataset, which was released last year. And actually, this figure is taken from the paper from Deepfake Detection Challenge, and shows how the different datasets have evolved in terms of number of videos, number of frames, but also number of subjects shown in the video, because these are 3 important parameters that indicate the variability and diversity of a dataset. This year, we also saw the release of the Korean deepfake dataset, which is even bigger in terms of number of videos and frames, but smaller in terms of subjects. And a bit earlier, 1 or 2 years ago, we also had the wild deepfake dataset, which was actually collected from the web. So it's a bit more representative of what happens on the internet. The Deepfake Detection Challenge was really an important landmark in this field. It attracted really massive interest, more than 2,000 teams, and it used 2 datasets, one public evaluation dataset. Part of it was accessible to teams for development and training purposes, and there was also a public leaderboard where teams could continuously post their solutions and see how well they did. but there was also a completely hidden data set, which was meant for the final evaluation. This challenge revealed a very big problem with existing solutions and the fact that they cannot generalize very well. And here we see how well the top 5 solutions did. And we see that when evaluating them with the log loss error, which was the official metric used by the challenge, we see a really big a gap between the public dataset, where we can see methods achieving performance below 0.2, and on the hidden set, the performance dropped by more than 100%. So the log loss exceeded 0.4. And this was a really big performance gap. Our team also participated in this challenge. We actually, when we started working on the challenge, this happened in the context of the We Verify project. It's an Horizon project that focuses on building verification tools for journalists. And we did quite well in the challenge. Our approach ranked among the top 5% of the solutions. And we have released the version of our service almost for a year now among the partners of the We Verify consortium. It has been already tested and evaluated in a number of iterations, and we are soon going to release it also publicly, but of course we can also make it available to AI4Media partners if they are interested. It looks like this, the interface we have developed. So when you want to analyze an image, as an outcome, you get a bounding box around the face and a score indicating the likelihood of the image being a deepfake. And in terms of a video, it's quite similar. There is an additional shot level segmentation. In this case, it's just one. And then the faces in the videos are shown in a clustered view, and they are shown per shot. And an overall deepfake score is presented. It's possible to hover over a specific face and see in zoomed detail of the face. And also, if someone wants to get into detail, they can see also the individual keyframes and the score for each of the keyframes. The service is a bit complicated as an implementation. It comprises a pre-processing step, a deep learning step, and a post-processing step. On the pre-processing, we have implemented a pre-processing approach based on face clustering, which seemed to work quite well and give a boost in combination with different models. Actually, we presented this in detail in the very first AI4Media workshop. And then for the deep learning part, we use an ensemble of models. We use 4 different models, which are variations of EfficientNet in combination with transformer architecture. And they have been trained largely on the deepfake detection challenge dataset. And these produce deepfake scores per face. So we build essentially a model around the face in each video frame. And as a post-processing step, we average the deepfake scores per face cluster and produce a final prediction as the maximum face deepfake score. And of course, we prepare the different results for presentation in the user interface. Here are some indicative examples of successful detection. They are all taken from existing cases from the web. So these are both successful non-detections. So the face is highlighted with a white bounding box. They are real and they were correctly not detected. And the ones which are with a red bounding box, they were correctly detected as deepfakes. Of course, our service also suffers from some limitations. So we couldn't properly detect the Tom Cruise deepfake, as also to our knowledge, no existing service was able to detect it. And that was because it was really high quality and it was generated also by extensive manual post-processing. Also, in our current service, we don't support fully synthetic faces like the ones coming from the "this person does not exist" service. And we also have trouble detecting very low resolution faces appearing in videos. And this is also another area we are working on. In addition to the previous limitations, it's also challenging for us to, put the computational resources for the training and for serving the requests. It is a demanding problem, and developing new models, doing research on it requires a lot of resources. And I guess this is a common problem among academic institutes that don't have their own cloud infrastructure available. Another challenge is the building a user interface that is easy to understand and make sense of, because this is supposedly used by non-experts and it shouldn't mislead them or create false impressions. And another emerging challenge is the fact that there are nowadays plenty of adversarial approaches which try to permute a single pixel or a few pixels and confuse the detectors. And as we saw before, generalization is a really big problem, and keeping up to date with new models, new methods, and continuously enriching the training dataset is a big problem. Here, actually, we show how big this problem is. This recent paper carried out some experiments testing different models on different data sets. So they trained an exception model on some specific generation models, and they tested on others, or they used a different data set to train and another to test. And in all cases, we see really big drops in detection performance. And to alleviate this challenge, the current trends include generating a variety of deepfake instances during the training phase and using those to enrich the dataset. Another group of approaches try to employ attention-based mechanism and also patch level consistency. Other ones try to use metric and contrastive learning during training time to improve the robustness of the models. And most promising, in our view, approach is domain adaptation and knowledge distillation, which is also an approach we are currently pursuing in AI4Media. We actually try to move beyond the simple teacher-student paradigm into a more complex group teaching setting, and also to make use of domain adaptive ensembling learning. Hopefully, in one of the next Work Package 6 workshops, we could report more details on that. And of course, there are at the same time many practical considerations like usability, efficiency, and maintenance that we are also working on and take into account. Thank you for your patience. I took slightly more time, and sorry for that. And I'm available for questions, or here are my contact details in case you want to get in touch offline.
Thanks a lot. We have time for at least one question. So I have one. Are you sure that Tom Cruise is real himself? One can wonder.
That's a tricky. I don't know. With so much makeup, you can not be sure.
Okay. Well, we have to further investigate this question. Okay, thanks a lot, Takis. And now move to another presentation from Dimitri Ignațiac from Barcelona Supercomputing Center, who will talk about the characterization of healthy discussions through temporal dynamics on social media. So, Dimitri?
Hello, let me share my slides. Can you see it?
Yes.
Okay, perfect. Okay, so my name is Dmitry Ignațiac. I work at High Performance Artificial Intelligence Research Group in BSc, and today I will talk about the research that we're doing in our group that relate to the project, and essentially to analyzing discussions on Twitter and trying to figure out which kind of discussions can be considered healthy. Before I start, just a brief note that in our group, we're mostly, backgrounds is artificial intelligence, and we have experience with high performance computing, so we're not really social scientists. So if you have any insights or you want to share some useful information, you want to participate, please, we're really welcome any forms of collaboration. So how this research has started? About a bit more than a year ago, when the COVID epidemic started to evolve into COVID pandemic, and countries started to introduce various measures, we decided to collect our data set of tweets, which I will describe in the next slide. And after we collected some of these, we started to think which kind of information can we extract from it. And we were particularly interested in whether it is possible to extract some healthiness information, some characteristics of healthy and unhealthy dynamics without using semantical information. And if it's possible, for instance, to see how some discussions evolve in time and to tell something about it. So speaking about the data, we have started to collect it at the end of March 2020. We used some COVID-related keywords, and we continuously collected it since then. Currently, we have over 1 billion tweets, which is pretty, well, from one point of view, it's impressive. From another, it's getting pretty hard to manage. And we have also wanted to allow secondary search queries over these tweets. So for instance, we wanted to divide this data set into topics. We wanted to have, for this data set to be, to support full text search. So we also moved these tweets to Solr database for allowing us to do these efficient text searches. Moreover, so after we gathered all of these, we have decided to extract some discussion topics to analyze these discussions. So we've took a look at Pointer's COVID-19 misinformation database. We've picked some of these topics that we thought were interesting and disputable enough. We have manually composed some Solr queries and extracted the relevant tweets. Furthermore, as tweets does not will not send you all of its tweets in response to queries, we tried to restore some of the discussion chains. So for all tweets in these topics, we have followed towards the parents until we've extracted as much as possible, because sometimes these chains are broken due to account being suspended or tweet being deleted. And after we got this, we have represented each topic as a temporal frequency vector. So essentially we have a vector of beans where each bean contains the number of tweets per this day. So what did we try to do with these topic vectors? So first of all, we tried some pre-processing techniques. We obviously tried normalization because some topics may have the same dynamics, but be of different interest to people, and thus have a different number of tweets. We've also tried some smoothing, which can be nice to smooth these high peaks, but at the same time, if high peak is characteristic to some bot activity, it may somewhat conceal it. So we try to do both with or without smoothing. We've also tried different time granularities, but from our experience, the day granularity worked pretty fine. And additionally, we also tried to align these topics because some discussions started at different time points and dynamics might be similar, but placed in different time periods. So we try different ways to align these topics. For instance, we try aligning them by highest peak, which is pretty simple and straightforward, but it is prone to, it's susceptible to noise, especially if the topic has several peaks of approximately equal heights. We've also tried center of mass, which is slightly more noise resistant, but for comparison methods that rely on these high peaks, it was obviously detrimental. And we've also tried time-consuming pairwise exhaustive alignment for each pair of topics, just to find this perfect alignment specific for them. And so having these, how can we measure how we can compare these topics? So we've used some, we've looked into ways it is done in some similar areas. So we've started with the most basic one, mean absolute difference. So we just, if we have vectors, we can calculate their difference, and that's it. It's obviously prone to noise, and Twitter is noisy, so it's not very well suited, but it should be there for baseline reasons. The one that worked pretty nicely is Kolmogorov-Smirnov statistics. Well, it's adaptation. Essentially, instead of using mean of all differences, we pick the highest difference. So essentially, by this measure finds topics similar if they have peaks of approximately similar sizes somewhere in the vector given the alignment. And there's also Jensen-Shannon distance adaptation, which is more smoothed version of KS, if I may. So instead of using just one peak, we also it composes mean frequency vector and compares each of topic vectors to it. Peaks, if peaks align, that's good, and that will get rewarded by this measure, but other days will also play some role. Now, I have some slides showing some of the results. I will not go very deeply into it. I just want to get an overview of, for instance, if we have Kolmogorov-Smirnov and we've aligned by max peak, it obviously finds similar topics with these high peaks that are of approximately the same size. But if we take, instead of max alignment, mean alignment, then it tries to approximate these shapes. It's not perfect, but it is somewhat more meaningful. And there are other options, and in order not to do these analyses by hand, which may be prone to mistakes, we have tried to apply some clustering techniques. So we have distance matrices, so we can apply clustering, and we tried, for instance, HDB scan, density-based clustering methods. And in most cases, it successfully extracted clusters. Let me see if I can get it larger. This should be. Oh, well, no matter. So essentially, they've successfully extracted clusters either that have some lone peaks or that are generally uniform and low. But with all this being said, it is still useful if we know that, for instance, some topic is good or healthy, or on contrary, bad or unhealthy. But the question is still, how can we define this healthiness? So we have currently one big candidate for the name of for being healthiness measure, and that is what is called ephemerality. Initially, it was proposed by our colleagues from CNRS for YouTube videos. Essentially, ephemerality shows how long does audience is audience interested in YouTube videos, how long it takes to accumulate most of its views. Now, with Twitter, it's a little bit more tricky, because for YouTube videos, they have the date of posting, so they have the predefined start date, and it's easier to do this. With Twitter, not so. And also with discussions extracted based on keywords, it may be prone to some accidental intersections. So how we try to adapt this? Well, yeah, obviously we tried the naive approach, just let's take it how it was and apply it. But as I said, it can both be prone to noise, and it does not really show us how topics evolve through time. So we can have, for instance, one high peak at the beginning and at the end of our research period, and it will have great value for this ephemerality measure, which would not correspond to, which would not be too healthy in reality. We can try to slightly avoid this issue by also cutting some percentage of tweets from the beginning. So say we want only tweets from 20% to 80%. And it might help, but it still does not contain any information about the evolution of the topic within this span. One way we found interesting to adapt this is to use sorted ephemerality. So for instance, if we take the topic and we sort its frequency vector and then apply ephemerality, then we first of all, we forgo the connection to the exact date, to the relations, to the dependencies between these frequencies and dates, and we can focus on how many days the discussion on this topic was actually active. Then again, it's still also not perfect. It cannot properly distinguish between topics with and without gaps, because it lost its ordering. So the best solution might lie in the intersection of the two. It is still open question, and we're working on it. So there are different ways we're thinking of how we may apply it. So from just having two values side by side, and if both are high, then probably it's the discussion is maybe healthy and proceeds nicely and does not have long peaks. If, for instance, unsorted is high and sorted is low, then probably they have a couple of these peaks, and it is definitely not healthy. But as I said, we're still working on it, and we are trying different ways to combine these into one nice healthiness measure. And that actually brings me to close to the end. So the things that we're trying to do now, well, first of all, we still trying to additionally process the data. If you paid attention to one of the first slides, the number of tweets extracted at different time points was not very uniform, so we try to compensate that, and by extracting additional tweets from Twitter using their Twitter academic API to compensate for losses, and select just a certain amount for when Twitter gave us way too many tweets. We also study different ways to work with this ephemerality measure, and we try to use it also in different ways. For instance, differences between ephemeralities might be used as a distance measure, and the point where we accumulate enough tweets, these 80% ephemeral 80% points may be actually used as, for instance, an alignment point. So that is ongoing. That is part of ongoing experiments. And there are also some bigger questions, like the definition of healthiness in Twitter discussion is still pretty ambiguous thing. And there are other interesting questions. For instance, should we only focus on original tweets? Should we somehow process differently shared tweets and so forth? Anyways, there's not much time left, so I will pretty much finish here. As I said, it was just a overview of things we're trying to do so that you get the idea. If you have some comments, you want to participate, you want to collaborate, please do. We're open to that, and we would really love to have the outside input. So thank you.
Thank you, Dmitry. Questions, please. So I have one. You've spent a lot of work collecting the really nice data set. What other applications can you see out of it?
Well, we we propose to share this data set with AI4Media's. So any kind of application that AI4Media partners do want to do, if they want, for instance, to analyze the attachment to tweets Tweets can have photos, GIFs, they can have URLs with texts. It is all there. We have it all, so we can share. And any way you can think of using the tweet datasets, we are open for collaboration and sharing it with the partners.
And do you see sharing as an option outside of the consortium? Because this might have a
yes,
large impact.
It might be tricky because Twitter does not, well, it might be tricky from the point of view of agreement with Twitter. So we can talk about it if there are some people wanting to do this, but we'll need to check the legality of that.
Okay, thanks a lot. So the next presentation will be given by Daniel Gatica Perez from EDAP Research Institute, and he will give us a glimpse at how people perceive news, so a human-centered approach to that.
Can you hear me and see me?
Yes, Daniel.
Hi.
Hi.
Good morning, everybody.
Morning.
Thank you for the introduction, Adrian. Interested in understanding how news are consumed in everyday life. And as we know, channels at different times of the day on their multiple constraints of how we go about our lives. And this is clearly an important problem. So today I wanted to focus on essentially two of the main motivations for the work we are developing in this work package. The first one, paying attention to the fact that news are consumed as part of an information ecosystem. And the second one, that specifically within the realm of news, local news are important, but are quite intricate. So let's start with the first part. I'm going to be quoting the work of Duncan Watts and collaborators who published a really good paper in 2020, where they evaluated the problem of understanding the issue of fake news, taking the whole information ecosystem into consideration. In other words, not only social media, but rather a very large-scale way of looking at things. In summary, what they did is the following. They analyzed two representative data sources coming from the US. One of the data sets comes from Nielsen, the company, and for that they analyzed a TV panel of about 100,000 people, and also a desktop web panel of about 90,000 people. And then the second source of the data they use is aggregated coming from Comscore, both the app and the browser traffic data. So these are hundreds of different news sources, hundreds of different media sources. And their goal is actually to understand, out of all this ecosystem, how much of this is news, how is it consumed, and how much of these consumed news are actually fake. Very important.
Daniel, the sound is very slow, so at some point we cannot hear you well.
Okay, can you hear me better now?
Yes,
okay,
much better.
So the first finding is that the daily US consumption of news is only a small fraction of all consumed media, specifically 14% of time. The second finding is that most news are consumed on TV rather than online. And this is a factor of over five times, also measured by time. And then the important third finding is that fake news corresponds to a tiny fraction of all daily consumed media. As you can see, there is just a fraction of 1%. So this is, in a way, a way of rethinking how much time we're investing as researchers looking at social media and fake news. By no means it's the end of the story, but there are quite intricate findings in this paper, so I'm going to go into a little bit more details. So in here, I'm showing from their paper on the x-axis the month of the year between January 16 and December 18. And then on the y-axis, you see the average minutes per day consumed over a number of sources. In blue, this relates to media that is not news, so TV, mobile, or desktop. Then on green, you see news, also from TV, mobile, and desktop. And then at the very top, you see this tiny red line that corresponds to fake news. So they reported that there's 7.5 hours a day that people engage in consuming media, including TV, video, music streaming, gaming, social media, etc. And as their first finding, it illustrates only a small fraction of this corresponds to news. Now, if we go into more details, here I'm showing two breakdowns from their paper. The first one shows results for online information. On the x-axis, you can see the different categories, and on the y-axis, the number of minutes per day. And you can see in red those that correspond to news, in green those that correspond to news, and in blue everything else. The bottom line shows the same kind of categorization for TV. And you can see very clearly the difference in terms of the number of minutes that are going to consuming news online versus consuming news by TV. So the more specifics, as the slide shows, is that there is an average of 54 minutes of news consumed on TV versus 9 minutes consumed online, so a ratio of 4.5. And there are quite striking trends depending on the age group. So for the very young people, you can see that the ratio is almost around 2. So 9 minutes versus 5 minutes, still TV is larger. And for the older segments of the population, the difference between consuming news on TV and online is even larger, over 7 times. Importantly, for the next point of the short talk is to see here how important local news are within what people consume as news on TV. Is roughly 40% of the news that are consumed. So clearly the question here is, what is the problem? If fake news are so little and occupy so little of our attention, why are they taking so much importance? And here I'm going to quote the discussion in the paper to go into their argument. So first of all, when they talk about TV, as they express, they are not objectively fake news stations, or the kind of sort that exist online. In other words, that they deliberately disseminate falsehood. But that said, on the other hand, misinformation can also manifest itself on TV or regular news in a number of forms, including selective attention, framing, spin, and other forms of bias. So one interesting question here would be whether working AI is actually trying to automatically detect this kind of not entirely falsehood, but ways of creating misinformation using practices that are known to exist in the media for many years. Obviously, there's a question of, even if the prevalence of fake news is quite low, it might be that they are disproportionately impactful. In other words, that they actually have more impact per minute of exposure, or that this impact is concentrated on specific subpopulations. And this is, again, a very interesting research question that needs to be addressed. And then the final point of their argument is that one should actually look more in the content of ordinary news, or the avoidance of news altogether, than in open fakery. And clearly there's something to be done that is not really about technology, it is about how we understand the intricate ways in which people consume media or not. They argue that public ignorance or misunderstanding of politically important matters could arise, for instance, out of ordinary bias or agenda setting in mainstream media, or the overall low exposure to news content in general, specifically in written form. So clearly capturing how we consume news in real life, it's a challenge. Here I'm showing a second example coming from Pew Research, where they essentially exemplify how a more holistic way of collecting news consumption could happen. In this case, they show a number of devices that people could engage to participate in a channel in a panel to collect news information. You can see that in this particular example, your personal computer or your personal phone could be tracked, but there will be other devices that might not be tracked, including your work laptop or the tablet you have at home or somewhere else. And that's not the end of the challenge. There's also the challenge that even if you agree to get your mobile news consumption tracked, there is the issue of whether you can actually track activity within specific apps or within all the activities in the browser. So this is just to illustrate that whereas the desire to holistically collect this information is there and is clearly important, is in practice quite challenging to achieve. More recently, Watkins and his collaborators have proposed a more ambitious research agenda on how to think about the news cycle and from the perspective of politics. So just to share one of the images in this position paper, they are looking at this pyramid that involves all the parts of the news cycle, from production to consumption and distribution to absorption and understanding to ultimately action and engagement by people who consume those news. And they argued that there is a need to both collect data from different sources and to actually think of different methodological approaches to understand what happens at each of the stages of this pyramid, and if desired, ultimately think of interventions to, for instance, improve the participation or the understanding of accuracy of news. So quickly, I want to move to the second topic of the presentation, which is about local news, which, as I mentioned here, are quite important. So roughly 40% of what people consume on TV, also a small fraction of what people consume online, but they are also intricate. And here I'm using data coming again from Pew Research, where they actually ask a panel of American citizens how they consume their local news. And you can see here, by local news, I'm talking about, you know, the local newspapers or your local TV stations, your local radio stations, where you get information from your city or your region. You can see here that the consumption is split among multiple channels. So again, the information gets split. And if we only focus on online, we're only capturing a small portion that is already clear from the previous study. And specifically for local news, people in journalism have studied this in depth, and they have found, for instance, that it is newspapers, so the printed versions that sometimes have online editions, the ones who are the most significant producers in the local communities. And here I'm going to quote work by Mahoney and others from the Duke Wallace Center for Media and Democracy, where they run a very interesting study that I'm going to summarize here in 1 minute. They first chose 100 local communities in the US. And based on that subset of communities, they actually labeled 16,000 stories coming from over 600 local media outlets, which included radio stations, TV stations, newspapers, and also others that only have online presence. And those stories were actually manually coded, annotated, as we would say in multimedia, with respect to a number of attributes, whether the story was original, whether the story was local, and whether the story covered a critical information need. And what they found was quite interesting. They found that it is actually these local newspapers that significantly outperform TV, radio, and online-only outlets in news production, both in overall story output, in other words, the number of stories that are produced, but also the number of stories that are original, local, and address a critical information need. So roughly speaking, 20%, 25% of these outlets, which are these local newspapers, produce 50% of the original news stories. Now, if we move this quickly to the context of Europe, there are additional challenges as it relates, namely to multiculturality and multilinguality, right? And this creates additional challenges for analysis because we will be facing necessarily multilingual corpora. But there's more. Also, Pew Research Center asked people in a panel whether they actually get local news from other local residents, and they actually found that 90% of people report to sometimes at least get local news from other local residents by word of mouth. And when people are asked more specifically, how do you get this information? So you can see that 71% is word of mouth, and only a fraction of that comes through social media. In other words, a lot of local information circulates outside any digital way of capturing it. Fortunately, people have been paying more attention to this issue of local news, specifically how to apply AI to local news. So just to conclude this quick intro, I'm showing a recent initiative by the Knight Foundation, who have decided to fund some projects that are looking into how to apply AI for media technology in the context of local news organizations. So I think it's timely also to think about these issues. So in summary, I hope I transmitted the importance that news need to be thought as consuming a larger information ecosystem, that this is feasible to study if you have connections with these big companies that study media, but it's challenging if you try to do it in academic research. Clearly, it will be interesting to understand what is the state of affairs, similar to the study that I talked about in the context of Europe, and also what part of AI4Media work could contribute to a better understanding of this ecosystem. The second point was, of course, that local news matter, and here I'm essentially asking for collaborations on the consortium partners to see how we could apply some of the technology that is being developed or will be developed in the near term to apply to this specific kind of content. Certainly, there will be need to think about adaptations, perhaps some redesign, and ultimately what could be a productive pipeline for one of the project outcomes. And as you can see, these are components towards the elaboration of a more holistic human-centered research agenda. Thank you for your attention, and I hope there's at least 1 minute left for a question.
Thank you, Daniel. Actually, we have a few minutes now. We are getting close to track. So questions for Daniel?
I have a question.
Please, Yanis.
Yes.
Sure.
Very interesting analysis, Daniel. Thank you very much. And yes, it shows an issue that in many cases does not take into account that local news shares some different properties than the, let's say, main news. Based on this analysis, are there any initial ideas for directions and approaches in order to tackle these challenges? What will you consider maybe best practices or something which is worth investigating?
Yeah, thank you, Janice, for your question. I see at least two directions. The first one has to do with some partners in the consortium imagining designing a corpora of local news to have some baseline to start applying some techniques and trying to see how these work. One of the questions is what kind of topics would be most relevant to start in the context of local news. And I think this would require a participatory process by which the different members of the consortium could talk about what their needs are. There have been some analysis at the level of surveys on what are the most recurrent topics in local news. There's a big question on whether false information also circulates in local news. So there's the need to define what the scope of that corpora would be. The second point has to do more with study, more using mobile technology, for instance, or also browsing technology to try to understand how actually people consume this news in their everyday life. And ideally, one could imagine a panel also across countries that could be based to actually have information of multiple countries across the AI4Media partners on how these local news are consumed. So I could see those two lines to pursue, and clearly there's scope to work on both.
Thank you very much. Very interesting.
Other questions? So yes, please.
Yes, Adrian, sorry, I had raised the hand.
Sorry.
Very interesting presentation, Daniel. I was particularly intrigued by these comments on the fact that simply classifying news as fake news or not is not a very good way to measure the quality of information that we get. And also these comments you made on the fact that we need ways to measure agenda setting, bias, and different kinds of very, hard to capture qualities of news is really important. Are you aware of any research efforts in that direction?
I think I have seen some initial work. I can't remember the specific references, but I think to me it would be important to partner with political scientists and journalists to actually look into if, for instance, some corpora are going to be labeled, what are the most appropriate ways of doing so, and also for what topics it is more appropriate.
Indeed.
Can I ask something as well?
Please do.
Hi, it's Yanis Padras from Queen Mary. I was surprised and didn't like very much actually that we have that there is this lack of analysis in Europe. If I understood well, are we going to try to focus then on how things are done here, and what do you think are the steps in that direction that we have to take in the project, perhaps?
That's a very good question. I think so. I have not given any thought in much depth about it. One possibility would be to see with our media partners whether there would be the possibility of having access to information of the same kind. And that seems to me indispensable to be able to say something meaningful about this topic. So this would require certainly the participation of companies to provide this kind of data.
Okay, so I think there are quite a lot of open questions which we can address during the discussion at the end. So
thank you.
Thanks again. So it is now up to me to present. Can you see my screen?
Yes.
Okay.
Yes.
I'll try to make it larger. So I will discuss some initial work about investigating the real life effect of personal data sharing. So this is work which is driven by some deep frustration. So deep is fashionable these days. So the frustration comes from the fact that we have all these privacy enhancement tools which are proposed, and they are most of them are not well adopted, and the main question here is why. So a possible answer is to say, okay, people are not adopting because they cannot understand properly how personal data sharing affects their real life. So we try to propose a modeling based on giving feedback about potential real life effects of their sharing. And we focused on visual content, which makes for a large part of data shared online. And we try to integrate with a situation modeling, which I will explain below. So first of all, I will speak about a preliminary experiment in which we try to compare the existing and proposed types of feedback. To do that, we select. So we have 4 situations that we modeled, and we selected 20 photos for concepts which are rated negatively in at least one of those situations, and we provided that to users who assume that they have an AI assistant which was dedicated to giving them advice about sharing or not sharing a photo which were they were about to share. So what we did is that we kept the interface identical, and we only varied the feedback message. So the interface looked kind of like this, a simple one. So we put the user in context. We asked them to assume that they were about to share the photo to the left. And then what changes is the message, which is in the green box, which says that, let's say current feedback would be that the app predicts that an image should not be shared because we detected a carrot in it. In this case, of course, it's a fake example. And then in our version, we say we have the same message, and then we add something like the carrots are negatively perceived when you seek an employment in information technology. So we give, simple explanation of why that image should not be shared. So we had 50 participants per type of feedback, and we quantified their answers in terms: would you follow the advice of the app? By 0 for no, maybe for 1, and yes for 2. And then we compute the averages of their responses. We get so 0.86 below 1 for the existing feedback, and 113 for the proposed one. So the proposed one is clearly more efficient. We've done some statistical testing for that, and this encouraged us to pursue this work. So the first thing to do is to model this whole thing. So what we have three main components there. So we have object detection in order to extract some meaningful information from photos. We have a situation model where we give a crowdsourced rating for each object in each situation, and we have a visual profile dataset where we evaluate the appeal of a given visual profile, so which is made of 100 photos in this case. So then we propose the learning-based method, which we proposed several methods, some baseline, which does a linear aggregation of the components cited above. We've done some learning based on compressed features, and then we have our proposal, which does rating based on new compression of the features. And we evaluate these different methods. So for the object detection dataset, we started by merging Microsoft Coco, Open Images, and ImageNet. We saw pretty quickly that that is insufficient. So out of 650 initial objects, we got 270 which seem to be interesting from a privacy-related feedback perspective. So basically, we will see afterwards. That means that they have objects which have ratings in situations which are not 0. What we've seen also is that many objects are missing. So I'm citing a few of them below, which could be interesting not to share. And what we did is that we started enriching the dataset. So we already have 80 of them annotating objects, supplementary objects annotated with 250 images per object, and we want to reach 1,000 and also to add some new supplementary ones. So now for the situation and profile modeling, what we did is crowdsourcing. So we have 4 situations. So we assume that the user is seeking for a bank loan, for accommodation, for an IT job, or a waiter job. We have 500 user profiles made of 100 users, which are all sampled from YFCC dataset. And we asked for annotation on a 7-point Likert scale. So between -3 and +3 for concept and for users. We had 14 participants for the situation annotation, for the concept rating situation, 9 for the profile ratings. We've done some statistical analysis, and we saw that the inter-rater agreement was within acceptable bounds for both tasks. We've done some analysis of the annotation results. So here we clustered the concept or profiles which have similar variation patterns across situations. So this is important to see whether a situation based to see whether there is variance between the way concepts or profiles are perceived across situations. So the results that we obtain clearly show that there is this variance. So it is relevant to model both concepts and profiles per situation. So to give feedback which is related to each situation. I'm providing some examples of high and low rated profiles. Of course, they are summarized. So for each for each situation, so there is not much surprise. So for the highly rated ones, we see people interested in cultural activities, in sports, in rather in food and drinks photos for the waiter situation. And for low rated ones, we see activities which can be related to violence or to risks and stuff like this. But the important thing is to see that these activities vary for different situations. And the surprise came from the fact, one surprise came from the fact that people who share their photos of babies are their profiles are rated negatively for the waiter job search situation. So about a short part about the method that we proposed. We model the profile rating as a supervised learning task, which allows the proposal of feedback at photo and profile scales. We try to avoid the curse of dimensionality because initially we had a lot of dimensions and not so much data per user. So basically what we did is to create a very compact feature with 3 dimensions per image. This is done by some clustering and then exploiting similarities between features and clustering used as final features, and then we train a random forest to rate the visual user profiles. We evaluated this on the data set of visual user profiles using the Pearson correlation. We got quite encouraging results, particularly for the method that we proposed. So we also evaluated with 2 different detectors. So RCNN, which basically can be deployed on normal GPUs, and then with MobileNet, which is only deployable, which can be deployed on smartphones because it's important to see what happens on at the edge. So for RCNN, we get correlations which are all above 0.5. For MobileNet, they are a bit lower, but not by that much. So the main finding here is the automatic profile rating is doable. Of course, it's imperfect, but doable, and I think there is quite a lot of progress to be made. We get good results with our methods. What we see is that bank and waiter are the most difficult and easiest situation to model. This needs further investigation to understand why. And of course, the larger object detector gives better results than the smaller one. So we integrate this into a mobile prototype app. So I'm showing to the left a global evaluation of the profile of a given profile in a situation. So this is done against a large collection of users. So basically, we have a score for each user in the background collection, and then we have the score of the current user, which can be placed, and then we can place this score against the others, and we see that in this case the photos have a slight negative impact compared to the average of the users. Then we have tiles where we show the images from those that have let's say negative impact to those that have positive impact using a traffic light metaphor. And then the user can click on the images and have detailed feedback about why that image was considered to be positive or negative in a given situation. And what we can see is that to the left, that the feedback, the valence of the feedback can vary from positive to negative depending on the situation for a same given image. So to conclude, this is the first attempt to model feedback about data sharing through its potential effect in real life. We introduced models and datasets needed to automate this task. We proposed the first learning-based method. We ran first edition of a related task at ImageClay 2021. And then we have the prototype app, which is briefly described at this website and its website, and then we plan to launch the app in September. So we delayed this quite a bit because we are still finding bugs and trying to correct them. In terms of future directions, we'll try to enrich the object detection dataset and to propose an end-to-end deep learning approach to profile detection. So that's it from me. If you have any questions.
Adrian, I have one question.
Please.
I was intrigued by your choice of potential jobs. How do you come up with that list?
Well, so we try to have 2 very different types of jobs. So the first one was so the IT one was because we kind of knew that we'll have quite a lot of people who know a lot about IT among the annotators. So we wanted to see whether there are differences due to the expertise and to our of the people who annotate. And to our surprise, there is very little difference. So between between annotators who are IT experts and people who are not IT experts. So the annotators are able to play the game, let's say. And then later we wanted to have a job which let's say wide part of young people could apply. So a kind of job which doesn't require let's say technical expertise. It's basically a side job or something like this. Of course, it would be good to have other types of jobs, but it's a bit time consuming to do the annotation, especially for the profiles. So for now we only have this two. Okay. And for the other two situations, we had some previous funding from people from insurance company in France. So they were interested in the bank and insurance. Also for the bank about the bank situation. We also tried insurance, but it was very similar to bank, so we dropped it at some point.
Okay, thank you.
Mm-hmm.
Adrian, thank you very much.
Yes.
Just a question out of curiosity. In the last example, if I understood correctly, among the negative in the red flashlight, I think there was a photo of someone doing paragliding or parachuting, something like this. Mm-hmm. If I understood it correctly, is this something that contributes to a negative point of view? And if yes, why? Or maybe I missed the semantics.
Yes. So the example was for people who are asking for a bank loan. And basically, what we saw there is a really clear pattern for a negative perception of, let's say, extreme sports or sports which imply some risk. Okay. So the question is very interesting because it relates to social bias, actually. So let's say normally we shouldn't have such biases, but what we noticed is that they occur.
So you take them into account.
Yes, of course. I mean, we take them into account, and if they occurred for the annotators, we can assume that they could occur in a more general population. So the message would be hide your photos doing a paragliding or whatever extreme sport whenever you go to your bank, and assuming that the bank has access to your photos.
Yes. Okay. Thanks. Very interesting.
Okay, thank you. Okay, so we are a bit late, and we can move on with the presentations and maybe get back to this during the discussion. So I would like to welcome Elena Kaushina from Queen Mary University, who will give us an overview of approaches for automated rumor verification and social media conversations. So, Elena, hello.
Hello, everyone. Thank you for inviting me. I'll now try to share my screen.
It's doing something. Let's wait for a few seconds. Yes, we got it.
Okay. Okay, are you seeing it full screen now? Yeah?
Yes.
Okay, great. Yes, hello everyone. So yeah, my name is Elena Kochkina, and today I'll talk about like existing methods for automated rumor verification in social media conversations, and about like the challenges that this field is facing. So I'll start with a bit of motivation for this work, and it's of course the fact that social media is used as So this is to do with social media being a very popular source of news nowadays. And of course, the absence of story verification gives rise to proliferation of misinformation on these platforms. And these unfiltered and often malicious posts can have a significant negative impact on various spheres of society. So a topical example, so along with the coronavirus pandemic, we are facing a so-called misinfodemic, widespread of rumors and conspiracy theories about COVID-19, which can create panic and it can affect rates of transmission, encourage trade in untested treatments, and all this effectively puts people's lives in danger. Another interesting finding from Reuters Institute is that during this recent year, news avoidance became more widespread. However, news avoidance is higher for the sources that rely on intentional exposure, such as television news, which actually have a step of story verification, comparing to sources that rely on incidental exposure, such as social media and messaging apps. So it just tells us how important this problem on these platforms. Traditionally, this is addressed manually by professionals like fact checkers, and recently there's been an increase in their efforts. However, manual verification is not scalable given the amount of misinformation being spread. And so that therefore there's a need for some automated system or systems that would assist in this process or in parts of this process. And this is why we turn to machine learning and natural language processing methods. So for the purpose of my talk, so here's the simplified definition of rumor. So rumors are check-worthy stories or claims that are unverified at the time of posting. So check-worthy means that they're verifiable, like we are able to actually say that this is true or false, and that it's important to know whether this is true or false. And also in this talk and in my work so far, I primarily focus on Twitter conversations. So here on the slide, you can see an example of a Twitter conversation discussing a false rumor. And this can attract all sorts of responses, some of which are supporting a rumor and some of which are denying a rumor. And so in this work, we view rumor verification as a classification task where a model is aiming to predict whether a rumor represented by a conversation is true, false, or remains unverified. So rumor resolution itself is a complex task and it can involve multiple subtasks. And on the slide, you can see a pipeline of tasks. Of course, it's an example. Some steps can be added or omitted. But well, this is a version of a pipeline that can be used for rumor resolution. So it can start with the task of rumor detection, where we identify those check-worthy claims, and it can be seen as binary classification task of rumor versus non-rumor. Then we would like to collect all sorts of sources that are discussing a rumor, and then to identify their stance towards a rumor, whether they are supporting, denying, questioning, or commenting. And then the final step is, of course, the verification, understanding the veracity of the rumor. So as you can imagine, with the high importance of the problem of rumor spread, rumor verification is an active research area in NLP. And I guess it also will be as no surprise to you that the dominant... hello?
Sorry, there is a small sound whenever someone connects or disconnects, so please allow for this.
Okay, yeah, I'll ignore that then. Yes, so yeah, I was going to say that the dominant methodology for dominant approaches are using deep learning. And so on this slide, these are various types of approaches with respect to which information is being leveraged. And I'm going to go through these approaches and also mention a recent study that utilizes this approach. These are not exclusive of each other, and a lot of works use a combination of these. So, of course, majority of existing rumor verification models utilize linguistic features. So, and this can be in different forms. This can be a text representation, starting from the simplest bag of words model, and nowadays more popular large pre-trained architectures, such as BERT. It can also be some manually defined features like presence of relevant keywords. So here, what I would like to note is that one needs to be careful when drawing conclusions about like the usefulness of such features, and to be careful whether they are being an artifact of a particular topic, of a particular data set. So this is the reason why the findings of different studies don't always agree with each other. For example, some studies are finding the use of sentiment useful to predict rumor veracity, and some are saying that it could not predict. And this could be to do with difference in the data and difference in how the sentiment itself is represented as well. And this is why it may be hard to make like a definitive judgment of which model is the state of the art, again, because it relies on different data. Rumor stories tend to develop in time, and they attract more attention, attract more opinion, more relevant information comes to light. And so rumor resolution can be seen as a time-sensitive process. And this, of course, gives rise to approaches that consider a timeline of a rumor with its growing context, as well as a structure of the conversation or a propagation path. So on the slide, you can see a model, like this is one of the earliest models that actually represented the structure of a conversation as a tree. So it relied on tree-GRU, recursive neural network. And yes, so it showed higher performance comparing to those approaches that ignored the structural component. So another important information that is often being leveraged is information about the user. So it can be represented as like features like number of followers, account age, and so on. But it also can be, users can be represented through their network of connections using following relationship or a retweet relationship. And so on the slide, you can see an example of the study that uses both a propagation tree encoder, as we've seen previously, and then also adds a user encoder to that. And the user encoders uses graph convolutional neural networks to capture user behavior. And it reports performance improvements when we're using both components together. Another line of work, and this was a big part of my work during my PhD. So a work involving rumor stance classification. So rumor stance classification is the task in itself to identify the attitudes of the responses towards a rumor, which can be supporting, denying, questioning, or commenting. And so why do we think that this can help us to understand whether a rumor is true or false? Well, this is to do with the fact that it has been shown by previous studies that rumors that attract a lot of skepticism are more likely to be proven false later. And yes, in fact, it has been shown that incorporating stance of responses helps improve performance of rumor verification models. And it can be done in two different ways. For example, it can be included directly as a feature, but also it can be used as an auxiliary task in a multitask learning setup. So here on the slide, you can see like an architecture of a multitask learning setup from our paper where we used stance classification and rumor detection as auxiliary tasks to improve rumor veracity classification. And this approach outperformed the single task learning approach, and it's actually, in fact, became very popular in the field. And I'll show more examples of the use of multitask learning. So you know, as I mentioned, these approaches are not exclusive, and people here on the slide, you can see the study that is using both a conversation structure as well as both tasks, veracity and stance together, and this reports improvement over previous approaches. And so the next couple of slides, I would like to show you like a very recent studies, or the most recent studies that I'm aware of in this field. So this one is from NACL 2021. And so this is also a model that uses multitask learning. However, it's using more complex architecture to represent the text. It uses a transformer encoder, and it uses multiple tasks from, I guess, the general domain of misinformation, such as news bias and clickbait and fake news. And what they have shown in their paper is that this kind of architecture can help, facilitates few-shot learning of unseen misinformation tasks or data sets. For example, I think they reported great performance on a propaganda detection task. And also they have tested generalizability to unseen events, and they reported very high performance as well. And then another type of approaches. So this is our recent paper from ACL Findings 2021. So here, this is a single task learning approach. And here we used a variational autoencoder to sort of disentangle the informational content of the tweet from the manner in which it's being said. So this has been achieved by obtaining the latent topic vectors in this adversarial learning setting. So where we used sort of stance classification task as an auxiliary task to sort of to obtain stance dependent and stance independent topic vectors. And then these latent vectors, then they were used to create a representation of a rumor and used in a veracity classification model. And so this led to state-of-the-art performance in accuracy on a clean data set. So another type of information that is, I guess it's a little bit beyond the scope of my current work, but it's also is a prominent line of research. It's, of course, the use of media and images. And so, yeah, so basically images can be manipulated or miscaptioned. And there's a lot of new challenges. So in a recent talk that I heard, as there's nowadays a lot of focus on deepfake detection. However, apparently the so-called cheap fake detection problem is still unsolved as well. So basically I gave a brief overview of existing approaches to rumor verification in social media conversations. And now I would like to move on to discussing sort of goals and challenges. So the ideal verification model, I guess this is our what we would like it to be. Of course, we would like it to be accurate, and you can see throughout talking about these various approaches, I always mention that they all strive to be more accurate than another. But also it should aim to generalize to unseen rumors. It should aim to resolve rumors at an early stage, because it has been shown that the earlier you can start the debunking campaign, the less impact the rumor will have. So something that really came to light to attention recently is the time-sensitive rumor resolution, because some claims, go from, for example, being unverified, and then they can be resolved as true or false a lot later. Also, in order to gain the trust of users, system needs to provide justification or explanations for its predictions and not exhibit significant biases. So basically, I'm going to try to address each of these points now and just try to maybe explain what kind of things are being done or can be done to address them. So not just to leave with open questions. So to address the problem of generalizability of models to unseen rumors, we need to make sure that we're testing our models on unseen rumors and topics. So for example, the approach we're using when working with theme dataset is called leave one event out cross-validation. So we train on events, like on a set of events, and evaluate on a different set of events. So the testing set contains a completely new vocabulary. Then, of course, creating larger training data sets that cover a variety of topics would be helpful, but I guess the question is whether it's ever going to be enough, because new rumors are always appearing on new topics. And another point is to search for topic-independent features that are indicative of rumor veracity. For example, the stance of the users. Because yeah, every rumor on any topic can attract support and denial, and those patterns are indicative. So in my current work that is related to COVID-19 misinformation, I did find that models struggle to generalize to this completely unseen event. I also so far found that actually increasing the training data size was helpful to help them. Yes, and another point on generalizability, that I guess this is likely to remain an issue because of an adversarial nature of the problem, where there may be parties who gain from spread of information, and we'll try to come up with new ways of doing that. Another important point is early and time-sensitive resolution. So one of the approaches that is existing is obviously testing model performance at different points in rumor timeline as more information becomes available. Search for features that present themselves at early stages of a rumor. For example, stance probably might not be this type of feature because early on users tend to be like adopting new information, and also we need to wait for like comments to brew to understand how people react to it. And of course, in the light of this, COVID pandemic, we see that something that was maybe false or unverified before might turn out true later, because like research on the topic is ongoing. Another like very important point is that systems should provide explanations, and this is what we always get when we start conversations with practitioners. Is that providing explanations is important to establish trust with end users. So this could be done through multiple various ways. Explanations could be provided through neural attention mechanisms or other explainable AI methods. We could also provide levels of model uncertainty, so for model to communicate to us when it doesn't know. So we tried that in our also recent paper on estimating predictive uncertainty for rumor verification models. Yes, so yeah, basically this is a very important point. And finally, checking for biases. So I guess this is, as all other models, is prone to various biases. For example, source bias. If a source is well established and generally trustworthy, should we trust everything that it says? And vice versa, if it's a small source or somebody created a Twitter account to report on what they witnessed, should we immediately distrust this? So this is another question which is tricky to answer. And of course, all this we believe should be done in conversation with practitioners and end users. And now at the end of my talk, I would like to also mention like my current project that I'm working on. So we came up with this nice acronym for it, Panacea, and we're focusing on COVID-19 related misinformation. So we have been collecting claims that are related to COVID-19, and we were also matching them with tweets that are discussing them and conversations. And so far, I've been looking at how existing models perform on these new claims, and going to be moving on to developing novel methods for veracity assessment. And so a big part of it is going to be incorporating evidence from external sources and not just from social media conversations. So these are like PIs of the project, my supervisor. And then another thing that I think is also relevant to mention to this audience is that there's an upcoming conference for Truth and Trust Online. And it's a platform where practitioners, academics, and platforms meet and discuss various issues of this field. And actually, so call for papers is still open, I think, for another month. And also, we recently got an agreement for a special issue. So authors of exceptional papers will be invited to submit an extended version of their paper to a special issue of the ACM Journal of Data and Information Quality. So yeah, thank you for your attention, and I'm happy to take questions.
Thank you, Elena. Thanks for this very nice talk. I think we have a hand raised by Georgia and also Akis. So Georgia, do you have a question?
Actually, it wasn't clear, sorry.
Okay, Akis.
Thank you, Elena. It was a really interesting talk. Actually, based on your work in Panacea, do you also handle cases where essentially knowledge, scientific knowledge and facts change over time? For instance, during the pandemic, we've seen several times where the recommendations by public authorities changed, and also new findings rendered the previous knowledge invalid. How do you handle those from a computational perspective?
Yeah, I have in fact mentioned this, that this is kind of a problem that in particular came to light during this pandemic. So currently, I guess we are, still at the beginning of the project, and we were focusing on data collection, and we were looking at the claims that already have been verified. But this is in fact something we're looking for. I guess this is to do with kind of constantly updating and having up-to-date sort of sources, or these like the evidence that your model is relying on. I guess so that would be my answer. So continually updating the sources and the evidence set that the model is relying on.
But do you keep only the latest label for such a so-called rumor, or the fact that at some point was considered actually true and accepted by official authorities should also somehow be recorded?
I guess this is a good point. So at the moment we just use the labels that like I guess the latest labels. So I guess if you come across about some claims that that will change, maybe yes, we will keep this in mind.
Okay, thanks.
Okay, Juana, you have a question?
Yeah, hi Anna, thank you for the nice survey. So I'm curious about two things related to rumors. One is do you have a feeling from where these rumors are coming, whether they are users themselves that they are promoting them, or whether they are coming from they are external kind of to Twitter, from news media organizations or blogs, and they just get reposted on Twitter?
I think both are the case. So I guess in my work I haven't looked closely into like the provenance of the rumors, but I think both are the case. In the data set I was working with, I saw a lot of information, yes, just like reposted from news websites, or the websites that claim to be the news websites that are like basically sources of various quality. And sometimes Twitter is used as a platform to spread misinformation campaigns as well. And also that, I guess, also uses bot accounts and so on.
Okay.
But,
okay.
Yeah, but I haven't directly incorporated this in my work.
Okay, no, I was just curious about these things. And the second, maybe more relevant for your work question is, what is the false positive rate of this rumor detection technique? If, for example, I take the state of the art technique now and try to detect rumors on Twitter, how many false positives will I get? Is it the majority of things will be false positive, or
right? So I guess for each of the different models, it would be very different rate of false positives, I guess, versus false negatives. So I can maybe tell you what I'm recently finding. So what I'm recently been doing is evaluating an existing model on this completely new COVID data. And interestingly, I found that, and I look at the 3-class classification setup, where we have classes that are true, false, and unverified. And interestingly, I found that the model that was trained on theme data set and is evaluated on this new COVID data is actually tends to predict a lot of unverified. And whilst this is not a correct prediction, I think it's not a bad prediction for this scenario, because the model is not strictly giving you the wrong answer. That is something that is false is true.
Okay.
Does that answer your question?
Now, do you think that if we have a set of tweets someone is reading, and we would like to understand how many of the tweets someone is reading are about rumors, do you think we could confidently apply some of these rumor detection techniques to find out, or it will be a huge overestimation?
Yeah, to be honest, for the existing models, I think the accuracy of them is very, very low. If we just apply this to completely new unseen data, at least this is what I'm finding. So I'm yet to recommend it to sort of be applied for public usage. However, I think things like claim detections or claim matching models, so whether we're given sort of a stream of tweets or a stream of information or news titles, you're trying to identify which things are check-worthy or which things already have been checked. So these kind of approaches, I think, are already being used by fact-checking organizations. For example, these are part of pipeline of Full Fact, which is a UK fact-checking charity.
Okay, cool. Thank you.
Okay, other questions? So I also have one, sorry. Do you look at the, let's say, cultural differences regarding what's a rumor or not? Because depending on the, let's say, country someone is in, something could be considered as a hard fact, and if you go somewhere else, it could be considered as a rumor.
Yeah, I don't look in this kind of cases, I guess. Yeah, so basically in our work, we sort of rely on judgment by journalists. So we usually work with annotated data sets, like theme was annotated by journalists, or the one that we are collecting right now is based on claims that are checked by fact checkers from, for example, Pointer website, which is, yeah, so I guess we don't really go beyond that.
I assume that if you ask from people from China to do the fact checking, you would get some different results in terms of what's rumor or not, depending on what let's say information they are fed with.
So yeah, I think this is a good point in terms of kind of how we choose who to trust in terms of fact checkers. Mm-hmm. So I think so Pointer is part of this, I think it's called International Fact Checking Network. Mm-hmm. So and they have these strict codes of conduct and the claims about their independence from government and companies. Mm-hmm. And then so the organizations under this umbrella, they are all sort of following that strict rule of conduct, and I guess therefore we choose to trust them. I have come across some platforms or websites that are claiming to be fact checkers, but they are funded by government, and they are, I don't know, for some reason only focusing on Russian misinformation. And so there I become slightly less trusting to such organization.
Okay.
So yeah, I guess this is the point to be made, just about importance of independence of fact checkers.
Ioannis, do you have a question?
Yes, yeah, actually I had a question that was very, very similar to you, and you are interested in, I was interested in what do you consider as a rumor? Is it a verifiable false fact, or is it a way of presenting things? Because of what Adrian has said, certain events have been presented and they are perceived in different ways in different circles, even between different countries, but even within the same country. When things are quite polarized, like considering things like Brexit, for example, or the Capitolium in the US. So, what is the fact that currently you're considering rumors, and do you think that the ways that you're trying to identify them, is it feasible to identify them based on the tweets themselves, or would you need at some point to resort to some external, like a fact checking, or match them with a fact checking somebody that is going to do that manually?
Yes, so first was on what was the rumor. So rumor, we consider that it is something that is verifiable. So it's a fact that can be, you can say it's true or false. I guess it's not an opinion. It's not something that, a sentiment about an event. So it's something that is a fact or can be checked, and it's also like important to check. And I guess we also say that rumor is unverified. So if you read literature about this, you will see that there's a difference in how different researchers define rumors. So in ours, basically, we state that this is unverified and can be resolved later as true or false, or remain unverified. So some other papers claim that rumor is necessarily false, but this is just like a definition, like quirk. Yes, so because we're approaching it from the perspective of supervised learning, we are relying on, this would rely on having annotated data sets. And so, of course, we collect like Twitter conversations or other evidence, but in order to make a judgment, like to make these annotations, like true or false annotations, we do rely on fact checkers, yes. However, I mean, I guess this line of work in general is trying to lead us to some systems that will assist fact checkers to perform this process faster. And so we would like to create the ones that provide maybe explanations instead of labels, like faithful summaries or basically explanations of its decisions, such that they're maybe presented to user or journalist in that way that it makes it easier to make a decision about whether this is true or false.
But sorry for following a little bit this up. Currently, you're trying to do this by analyzing only information in the media where these rumors have been, or these things that you want to classify there as rumors or not, have been presented. So you're analyzing only the Twitter feeds, for example, or you're trying to match those with some data that come from some authorities, for example, from the World Health Organization, or from some medical journals, or that's what I'm trying to understand that a little bit.
Yeah, so this is part of the Panacea project. So in my work so far, before, I was only looking at Twitter conversations. So yeah, the information was just limited to that conversation. But in this project that we're currently working on, this is what we're doing. Yes, we're trying to incorporate into the verification model information from social media, and also from more reliable sources, like you mentioned.
Okay, so Thanks a lot again. And well, given that there is quite a lot of discussion on the topic, I hope you'll be able to join us in the discussion at the end to continue this discussion. It's time for a break. Let's say 15 minutes break until 11:15 and reconvene then.
Hello, my name is Georgios Zomboulis, and I will present you our joint work with Ioannis Patras, which is entitled Pairwise Ranking Network for Affect Recognition. Next slide, please. So in general, emotion recognition is a task that can be served from multiple modalities, such as the visual modality that can contain facial expressions, body pose, hand gestures, and others, the audio modality that includes human speech, neurophysiological modalities such as the EEG signal that contains brain activity, heart rate, skin resistance, and others. Now, to recognize emotions, we first need to annotate them, and for this purpose, various emotion modeling schemes have been proposed, with the most dominant ones being Ekman's categorical scheme and Russell's dimensional scheme. In Ekman's model, to model emotion, In Ekman's model, in the previous slide, please. Okay, in Ekman's model, emotions are labeled in a categorical way in classes such as angry or happy, and in Russell's model, emotions are decomposed in the two dominant dimensions of arousal and violence, with arousal referring to how intense or calm an emotion is, and violence describing how pleasant or unpleasant an emotion is. Next slide. Now, of course, the modeling scheme that we choose to model emotions and also the quality of the annotations has an impact on the machine learning models that we train using these annotations. So, for example, if we choose to use categorical annotations, we may have some drawbacks, such as the fact that we cannot capture intensity level details, and also we cannot express the possible compoundness in the nature of emotions, such as to infer the difference between happily surprised versus sadly surprised. Another thing is that by using categorical labels, we have the drawback that our trained models may not be able to infer ordinary relations between samples. So, for example, to say that this sample has a higher arousal than the other sample, so to compare in a pairwise manner two samples. So, as a remedy to these drawbacks, there has been proposed the use of dimensional labels. However, again, there arise new problems, such as the fact that each annotator has his own subjective bias, his own perception of affective stimuli. And again, even considering a single annotator, the perception of the rating scale may change across time, because, of course, we judge the affective stimuli based on the temporal context that has been shaped by our previously encountered affective experiences. These dimensional labels are usually collected by assigning numerical values in a continuous rating scale, so the perception of this rating scale changes both for a single annotator and across annotators. Even more, if we try to use dimensional labels, however, by adapting them to a classification approach, by inserting some class splitting thresholds, these thresholds are usually arbitrarily selected by researchers to help for classification approaches. So this inserts another bias. So actually all these observations drive our motivation to treat emotions as being ordinal. Hence, we aim to explore the ordinal nature of emotions, and instead of inferring the affective state of a single sample, we propose to consider samples in a pairwise way and to try to infer ordinal relations between samples. Next slide. So the traditional way of performing emotion recognition in a sample-wise manner is that samples are fed in a backbone network, which we name embedding module, and this network extracts sample-wise features. And then these features are fed ultimately to a classification or regression module, depending on the end goal task, which can be classification or regression, to infer the affective state of a sample. However, when you use dimensional labels, these are assumed to be absolute. However, this is not true, as the perception of the annotators changes across time and across annotators. And also, there's another problem that we ignore intersample relations, which cannot be captured by operating in a sample-wise manner. Next slide. Next slide. Okay, thank you. So we take another approach, and we suggest a network which is trained jointly on classification or regression and on ranking task. So we use two tasks, and actually the first task is the traditional task of classification or regression, which is done on a sample-wise manner. And the second task is the task of ordinal ranking, which is a pairwise task. So to do that, we do not operate on the raw samples, but instead we operate on the features that are extracted from the embedding module for each sample. So the feature representation for two samples are concatenated, and then they are fed to the ranking module, which learns to infer an ordinal relation between the two samples. We consider three cases, where the one case is that these two samples, with respect to their effective labels, have similar ratings, meaning that their labels are close in the label space, in the bounded range. And the other two classes are that the two labels are, the one is lower than the other or higher than the other. The ultimate goal of including this additional task during training, the ranking task, is to boost the model performance on the other task, which is classification or regression. Next slide. The total loss on which we train our network is the sum, of course, of the classification or regression loss and the ranking loss. We also add the hyperparameter alpha to weight the contribution of the ranking loss in the optimization of the total network. Our classification loss is a typical cross-entropy loss, with the labels being, for example, low versus high arousal or violence. And the regression loss is a typical mean square error loss, which optimizes the mean square error between the predicted and the ground truth continuous values. Our ranking loss, again, takes into consideration the three ordinal classes that we mentioned before. The network is trained in an end-to-end manner, hence the gradients from the ranking task also flow all the way back to the embedding module. In this way, the weights of the embedding module are updated so that they serve not only the classification or the regression task, but also the pairwise ranking task. So our aspiration is that by this way, by exploring the intersample relations through the ranking task, our embedding module will be able to explore in a better way the structure of the dataset with respect to the label space, and also take into consideration the ordinality that exists in the space of emotions. Can we go to the next slide? Okay, so to derive the ordinal labels for a pair of samples x1 and x2 with corresponding labels y1 and y2, in the case of those labels being continuous, we define a hyperparameter epsilon, which we name as rank tolerance. And in the case that the distance between two labels y1 and y2 is lower than epsilon, the absolute difference, then we consider these two labels as being similar. And this is the one of the three cases that we include. And the other two cases, based on this continuous range, are that the pair of the samples has a label of high ratings, y1 is higher than y2, and the other one is lower ratings. We opted to choose this third class of the similar ratings, in contrast to previous works that operated on pairs of samples, that consider these comparisons as unclear and discard them from training. We will see later the impact of this. Can we go to the next slide? Okay, so we used three datasets in our study. The two datasets, DEP and SID, contained EEG signals, while the third dataset, AffectNet, contained images of facial expressions of persons. All these datasets differ in various aspects, such as the process that was used to collect the annotations, also the annotation values, and also the end goal task, where the end goal task for the EEG datasets was classification, and for AffectNet dataset of facial expression images was regression. Can we go to the next slide? So, the task that we tried our approach on was emotion classification on depth dataset. In this dataset, the inputs are EEG signals that have been collected from participants that were viewing music video clips, and the participants rated these video clips using self-assessment questionnaires in a bounded continuous scale from 1 to 9 for the attributes of arousal and valence. Then the end goal task is classification. So to perform classification, we split the label space into the middle point of 5, and we consider the two classes of low or high arousal and valence correspondingly. Of course, this approach disregards completely the ordinal relation between pairs, even between pairs that may lie in the same class. So, for example, for two samples that may belong to the class of low arousal, or even between samples that may belong to the two different classes. Our baseline model was a simple MLP-like architecture where the embedding module had stacked fully connected layers, getting EEG features. And again, the ranking module was an MLP network that learns the deep distance measure. And we can see from our results that by incorporating the ranking loss as an additional objective during training, we can have benefits both for the accuracy and the F1 score in this dataset. And specifically, we can pay more attention to the F1 score due to the label imbalance in this dataset, which makes the accuracy measure less important. And we can see that considering the inter-sample relations and not just disregarding them by splitting the classes and adopting plain classification boosts our performance. Next slide. The second dataset that we tried our approach on was SEED dataset, which again contains EEG signals from participants that were viewing movies. The three classes, the three labels in this dataset are neutral, negative, and positive. So, of course, there is an evident ordinality in these three classes as they correspond to different levels of the valence emotional attribute. This is totally disregarded by previous approaches. So to adapt the scheme that we derive the ordinal labels from our original labels, we have to adapt it because our original labels are discrete and not continuous. So we adopt the assumption that the positive label succeeds the neutral and the negative, and also that the neutral label succeeds the negative label. Now, training our model by incorporating the ranking loss in this task again, we can see that we also have performance boosts in the accuracy and F1 score. And this means that our scheme that we derive ordinal labels and our incorporated ranking loss also helps even in the case where these labels are discrete and not just continuous. Next slide. The third dataset that we tried our approach on was a regression of arousal and valence in the AffectNet dataset. In this dataset, the images depict facial expressions of humans, and they are annotated in arousal and valence in the range from -1 to +1. So we adopted the evaluation measures of root mean square error, of the Pearson's correlation coefficient, which is denoted as PCC, and measures the correlation between the predicted and the ground truth distributions, and the concordance correlation coefficient, which is denoted as CCC, and it is a more strict and well-representative measure to measure correlations because it also considers the offset between the average values of the distribution of the predicted and the ground truth labels. So again, we derive our ordinal labels in the same way that we used for the DEAP dataset, and we can see that incorporating the ranking clause and also our baseline network is a VGG-like network with stacked convolutions, and we can see that by incorporating a ranking module and the ranking clause, we can have performance benefits on all measures, and this is important because our default loss was MSE, which optimizes explicitly the RMSE measure, and we can see that even the RMSE measure, by incorporating the ranking clause, can be improved. Next slide. Now we performed some ablation studies to get some insights on the functionality of various hyperparameters of our method. So the first hyperparameter that we tuned was the hyperparameter alpha that weights the contribution of the ranking loss in the total optimization objective. Of course, the default scenario where we do not use ranking is the case where alpha equals to 0. And the default scenario for all the previous experiments on ranking had the value of alpha fixed equal to 1. We can see that by increasing the value of alpha up to 5, we can have performance improvements in all measures, both for arousal and valence. Another hyperparameter that we tuned to get some insight was the hyperparameter epsilon that defines the distance in the label space that we use to consider two samples as having similar labels. We can see that in the default scenario for AffectNet, this value was fixed equal to 0.15, and we can see that for increasing it up to 0.3, we have performance boosts for all measures, and both for arousal and valence. And this somehow validates our previous choice that we chose to include these pairwise comparisons for these samples and not to discard them as being uncertain comparisons. So we can see that the embedding module benefits from the gradients of the ranking loss by including such pairs, especially in the dataset of AffectNet that has quite noisy labels from various annotators. Next slide. So the last thing that we tried on AffectNet was an ablation study where we restricted the range of the training label space and also the cardinality of the training set. So we chose to shrink the training set by defining a hyperparameter to cut off the label space of the training set, so that by looking at the figure on the left side of the slide, we keep only the training samples that lie within the green range of this figure, so that if the absolute value of any of the labels for arousal or valence is larger than C, then we discard this training sample. Of course, the case where C equals to 1 refers to the case where we use the full training set, and as C decreases, also the training set size decreases and the label space that we use to train decreases. In all cases, we evaluate on the full validation set, so we again have the full validation labels, which has been unseen during the training phase, and this helps to get an insight into the generalization abilities of models that have been trained by incorporating the ranking loss. We can see that as the training set decreases, of course it is expected that the performance of all models will decrease, but we can see that models that have been trained by incorporating the ranking loss are more robust to such shrinkage of the training set. Next slide. So concluding, we showed that treating emotions as being ordinal is very crucial for various cases of emotion recognition. And we showed that in a very simple way that can be incorporated in all types of deep learning architectures without any problem for the rest of the functionality of the architecture. We can propose the ranking supervision as a helpful objective during training. And we can see that we can have performance boosts on various measures, such as accuracy and F1 score for classification tasks, and such as the measures of root mean square error and Pearson or concordance correlation for regression tasks. And we also showed that this can help for various types of annotations that have been obtained in various ways. That's all. Thank you.
Okay, thank you. Questions, please?
I have one question.
Mm-hmm.
Thank you for the presentation. If I understood correctly, you use existing annotations and then you turn that into the pairwise ranking case, right?
Yes. the key issue here is that these annotations have been collected in a sample-wise manner. So actually to apply perfectly the concept of pairwise ranking, one would have to collect a data set by having persons to label pairs of samples. So for example, to view two images and rank them as such. But of course, none of these data sets had such types of labels. So we had to derive them on our own.
So that was actually my question. If you were to annotate this, bringing in new observers and asking them to rank pairs of images, what would be the right setting and what could be the expected reliability? Would it be expressions of the same person or pairs of different people? What would be the right experimental setting for annotation?
Yes, that's an open issue, but it's very interesting, of course, because it affects reliability of the labels very much. So, in my opinion, it's not that you should have an annotator to label the facial expressions of a single subject. He could label the facial expressions of as many subjects as possible. But two key issues are these. The first one is the temporal window, where he might encounter some experience that he will be asked to rank. So, for example, you cannot have a subject to see 10 videos in a row and maybe 40 videos in a row and then ask him to rank all of these videos. You have to shrink this window that the subject encounters this stimuli. And another issue is that for maybe for these labels to be valid, you have to avoid, let's say, mixing various annotators. Because in our case, for a FakeNet dataset, we also trained our models on labels that were obtained by multiple annotators. But this is an open issue on how because still an annotator may have a subjective bias in a sample-wise manner, but still he might have also a subjective bias in a pairwise manner. So how to mix these obtained annotations from multiple annotators, it's an open issue.
Okay, thanks a lot. We are running a bit late, so we'll go to the next presentation, which will be given by Gabi Constantin and will be about DeepFusion, so system DNN system ensembling. Gabi?
You hear me okay? Can you hear me? Okay, so hello everyone. Just let me know if you can hear me and if you can see the presentation.
Yes, we can see, we can hear you quite okay. So.
Okay, thank you. Just a second. Okay, so hello everyone. I am Gabi Constantin from University Polytechnic of Bucharest, and I'm going to talk about DeepFusion, which is our platform for deep neural network-based system ensembling. So just a basic introduction in the domain. Ensemble systems consists of systems that exploit outputs, prediction outputs from individual systems called inducers, and they use an ensemble algorithm in order to combine the prediction outputs of inducers and improve the overall performance. In our opinion, what we created here is particularly useful in cases where inducers have unsatisfactory performance. So far in the literature, several types of ensemble algorithms were created, starting from statistical ones to boosting, different types of boosting or bagging, and so on. So basically, deep neural network side of this is largely unexplored. This is what to create and use the DNs as the primary. We will add attention layers. After this, we will process the input, or we call it representation layers. Add convolutional layers to the architecture, again, in order to increase performance. And finally, introduce a newly created layer called the cross-base fusion that processes the decorated input in a special manner. So the basic problem formulation is the following. Given a set of inducers, which we call F, and a set of samples, which we call S, as you can see, each inducer creates a prediction for each sample. And the problem that ensemble systems are trying to solve is to create a new function called E that will create a better set prediction for those particular still okay here.
Not very well. Can you shut down the video maybe, just to see what happens?
Okay. Just a second. So, is it better now?
For the moment, yes.
Okay. Okay, let me know if there are any other problems. Starting with a basic dense architecture, as you can see, the input of this architecture is created by joining the prediction outputs from the inducers. For this particular architecture, we vary the number of dense layers, the number of neurons per layer, and we either inserted or we took out batch normalization layers. So it is quite a straightforward architecture. For the attention architecture, we took the best performing dense architectures and we augmented their performance with attention layers, more precisely with soft attention with values between 0 and 1. Talking about input decoration, as you can see, for each individual sample, there is no information in the vector of predictions created by the inducers. There is no information related to the inducer correlation. More exactly, there is no spatial information. Therefore, applying any type of layer that would exploit spatial information or input decoration would not work on this form of the input. So what we have to do is calculate, first of all, calculate inducer correlation on our training set. So basically for each inducer, we can create a set of a vector of correlated inducers by calculating pairs of correlation. These are denoted with C, C1 being the most correlated inducer and Cn-1 the least correlated one. Also, we can, of course, calculate a vector of correlation scores, which is denoted R. So, regarding the convolutional architecture, what we can do in this case is decorate the centroid, which represents each pair of sample and prediction outputs, with prediction outputs from the top four most correlated inducers and their respective correlated scores, using the same C and R notation I've presented before this. This is how such a decoration would look like for a single sample. So again, our target here is to boost the performance of the top performing dense architecture with convolutional layers. And what we can do here is vary the number of convolutional filters that we input into this architecture in order to get a better result. Again, the architecture starts from the input, which it decorates, passes through the convolutional layers, and then through the top-performing dense architectures. Next, for the cross-space fusion architecture, we decided to separate the correlated inducers from their correlation scores. So basically, instead of just one single centroid, we now have two. Each sample and prediction output is decorated with prediction outputs from the most correlated inducers. And in the second index is we have the correlation scores. In this case, given a decorated input of size and n times m, two-dimensional, basically a two-dimensional input, what we will obtain is a three-dimensional decorated input. This decorated input is then passed through the CSF layer and again through a pooling layer that will allow it to be passed to the dense architecture, and then we will have the final score. So the variables in this case can be represented in our experiments by the number of populated correlation. What the CSF does is learn a set of alpha and beta parameters for each centroid. And as you can see in this matrix, the alpha parameters are used to moderate the prediction output, while the beta parameters are used to moderate the correlated prediction outputs and the correlated scores. So our use case for this presentation is represented by the prediction of media interestingness. For this case, we use the part of the interestingness 10K dataset, which is represented by the medieval 2017 predicting media interestingness task. This task was split into an image and a video subtask, and what we used in this case as inducers were the systems sent by the participants to this task. So we had 33 inducers for the image task and 42 for the video task. However, given that the participants submitted files only contained prediction outputs for the testing part of the dataset, we had to create new data splits on these files, and we created two data splits: a random stratified keyfold where 75% of the data is used for training and 25% for testing, and a 50-50 split. What we did is create these data splits a large number of times in order to avoid, let's say, lucky splits. And in the final version of the experiment, we had 100 partitions. This means 100 runs for each combination of our proposed networks. We also tested some basic traditional ensembling techniques that are trained and tested in the same way as our method, in order to compare our method with traditional ensembling approaches. So these are the results for both image and the video subtask. What you can see on the yellow rows are the state-of-the-art on the medieval dataset, and these also represented inducers for our systems. What you can see in the blue rows are the best results for the traditional ensembling techniques, and the green rows show our results. As you can see, the best performing systems are either convolutional or the cross-space fusion layer. The results improve the state of the both the state of the art and the traditional ensembling methods by a large margin. So some conclusions and future works and thoughts with regards to this. As I said before, improvements can even go over 100%. We also tested these methods on other data sets and tasks, either from other medieval tasks or from image clay. You will see some of them in the reference slide. And these were perhaps even different types of tasks, meaning for the interestingness task, we had a two-class regression problem. However, we also tested them on two-class classification or labeling tasks, and they performed well as well. Of course, there is a trade-off with regards to hardware requirements, because in a real application, let's say, you would have to run each system, and each inducer, and this would create higher hardware requirements. However, this approach can push a task towards a market-ready status in case the individual inducers are not good enough to be considered market ready. So what we want to do for the future, of course, there is also the option of improving the network architectures for our proposed models. But we are also planning to look into optimization with regards to the number of systems we use. So the question here is, can we find an automated method of dropping some of the inducers and therefore minimizing the hardware requirements, and while of course also keeping good results. Another question is, can we create a package of out-of-the-box inducers, for example, a set of well-known and well-used inducers that can be applied in a larger set of experiments without someone having to worry about the particularities of the task. The question here is, can something like this work? And of course, in the future, we will work on creating a Docker container that can be easily distributed to those who want to test our methods, or who want to apply them to their particular task. So finally, three references here. All of them are published in the AI4Media project. And these represent several stages of our experiments and of our DeepFusion framework, and their application to several tasks and data sets. So thank you very much.
Thank you, Gabi. Questions, please. So I have at least two. So the first one would be, did you look at what happens when you have a smaller number of inducers in terms of the effect? So when you override number of inducers, because for the task that you presented, you have quite a lot of them in the input. So what would happen if you have, let's say, 3, 5, 10?
Okay. So what we did in our publications was take the number of inducers that were available during the respective data sets and tasks. We are planning to find a way of automatically going through them and let's say only keeping those that really help the system, and taking out anything that has redundant information. I can take a quick look through our experiments and tell you that the minimum number of inducers we used for a task or a data set is, just a second, 13.
Okay. A second question is that from the task that you presented, the problems at hand seem to be quite simple in terms of number of classes to in the output. So did you try it for more complex tasks where you have a much larger number of predictions which are possible?
Yes, we did try it for the labeling task for image claim medical.
Mm-hmm.
There is a large number of possible labels there, and one image, one sample can belong to can have a large number of labels. And in that case, we also had we also increased the results by somewhere around 40%.
Okay, that's very good actually.
Yeah.
Okay, other questions? Well, if not, we'll take the further discussion to at the end, and I would like to welcome Juan Agoga from the French National Center for Scientific Research. She will tell us about why it is difficult to detect political ads online. So.
Thank you, Adrian. Is this okay?
Yep, we can hear you right. Yes, we can hear right. We can see the slides. All fine.
Okay, cool. Sorry, so my webcam died a few weeks back, so it will be just the voice for today. So yeah, today I will talk about two projects that we did related to the detection of political advertising online. So now I'm assuming that everyone has received online ads, but maybe not everyone knows how online advertising works internally. So there are basically three things that you need to know about online advertising. First is that everyone that has a credit card can be an advertiser. Okay, so if you have a Facebook account, in a matter of 3 clicks, you can already send an ad to someone to the world. The second thing is that Facebook has over 200,000 attributes available to micro-target users. So advertisers can choose to target people that are interested in anti-abortion movements or in cancer awareness or other 250,000 weird attributes that Facebook is offering them. And the third thing is that Facebook has over 2.5 billion users, and other social networks have also a large user base. And I'm saying this to understand that anyone on Earth can actually directly talk to any of these 2.5 billion users by paying Facebook to send their ads. Now, the second thing that is important it's an important observation is that we are seeing a shift from using ad tech to promote products to potentially interested people. So here are a bunch of tennis shoes because you search things related to tennis, and we are actually seeing an increasing number of advertisers that target well-chosen information to specific groups of people likely to accept it. For example, you can send articles about vaccine side effects to people that might be skeptical to get vaccinated. So this ability to target information can bring new dangers from our democracy, and we actually saw several misuses of this ad technology during presidential election, which was especially in the US. So probably the most known scandal was Cambridge Analytica. So what Cambridge Analytica was a political consultancy firm, and what they are known for is that they targeted people with ads based on their personality. And this happened before the 2016 election in the US, but also they did the same thing with the Leave EU group before Brexit. And here you can see, I mean, some of the ads they send in the US. Now, the second misuse of ad technology before election was the foreign interference through political ads. So again, before the 2016 election in the US, the Russian Internet Research Agency sent several ads and you can see some examples here in the image of their ads, and we know that they were on polarizing topics, were targeted at precise group of people such as African Americans and Latinos. So these two big attacks and scandals actually made people realize that it's possible to weaponize ad technology to engineer polarization, to promote voter disengagement and manipulate users to probably choosing one candidate over the other. As a response, ad platforms and governments as well have started to adopt some countermeasures. For instance, Facebook implemented this ad library for political ads. So there is a library, a central repository that contains all political ads that can be publicly accessed by anyone to check what political ads are sent on the platform. And they also have a range of measures such as same country policy, meaning that you can only send political ads in the same country that you reside, and you can prove that you live there. So this is like on the ad platform side, but also governments are trying to step up and and take some action. So in the European Union, they are working on two pieces of legislation: the Digital Services Act and the European Democracy Action Plan. Like GDPR was the big legislation that they were working on 10 years ago. The current two big legislation that they are working on are these two, where they are trying to regulate online platforms in general, but also they have they are also focusing quite a bit on online advertising. And from the last declaration of Vera Jourova, which is European Commission Vice President, they are seriously considering to limit micro-targeting as a way to promote political messages. Yeah. So this if you look both measures from ad platforms and governments are going into the kind of the right direction of trying to protect citizens, but the problem is that everyone makes the underlying assumption that we know which ads are political and which ads are not, because all these measures that are proposed here, either by ad platforms or governments, are only focused on political ads. Yeah. So and yeah, this assumption has not been tested in practice actually. So the way we started to address this problem first was by taking an audit perspective and see if the Facebook ad library it's missing political ads. So the Facebook ad library is supposed to contain all the political ads on Facebook. So our question was whether this library does contain all political ads. And for this study, we focused and we did the data collection before the Brazilian 2018 election to take it as a use case. So this is how the Facebook ad library looks like. As I was saying, it's a central repository for all political ads. But the important things to know is that advertisers need to declare on a voluntary basis if they are sending a political ad or not. So when you send an ad, you have this question where Facebook it's asking whether your ad is political or non-political. If you click that is political, the ad will appear in this central repository. But we don't have any public information about if or how Facebook enforces this policy. For example, if I don't want to declare if I'm sending a political ad, but I don't declare it as such, will Facebook detect it? Will Facebook force me to and put it in this ad library? So we actually don't know to which extent advertisers comply with this policy. So we don't know how many political ads are missed from this ad library. So when we are doing this kind of empirical research, the big challenge is access to data, because we actually don't know to what ads people see on Facebook, and we don't know whether they see political ads or not. So what we did for this study is that we build these independent auditing platforms that enables the participation of the society by donating data about the ads that they receive on their Facebook timeline. Yeah, so we build this platform. We build this platform that is called Ad Analyst. That it is in the form of a browser extension that users can install on their browser, and observes the ads that they see when they browse their timeline and sends them back to our servers. So to the most important component in this kind of auditing platform is, of course, users, because if we don't have data from them, there's not much we can do. So to convince people to install our extension, we wrote a bunch of opinion articles in Brazil. I mean, my co-author who wrote these articles, because he's Brazilian, and we also presented this tool in the Brazilian Senate and was part of a task force for protecting legislation in 2018. And as a result, we had over 2,000 Brazilian users that volunteered to install our tool. So in terms of the data that we collected, is that we collected over 239,000 ads coming from 40,000 advertisers before the pre-electoral period and electoral period in Brazil. So this is a sample of ads people see that they are both political and non-political. Yeah, this is the ad analysis data set. And then we also collected, of course, all the ads that were shown in the political ad library, the official political ads in Brazil, and there were about 100,000 ads coming from 5,000 advertisers. Yeah, so this is the data set that we collected, and now that we have the data, the traditional way to detect political ads or whatever is that you take a bunch of political ads, the positive examples, the bunch of non-political ads, the negative examples, and then you can feed them to a supervised machine learning algorithm to obtain a model for what is political and what is non-political. But now the key to this whole process is to get a good and representative examples of the two classes of political and non-political ads. So in this paper, for what we decided to do is that as examples of political ads, we use data from compliant advertisers that are already labeling their ads as political. Yeah, so we took a sample of 10,000 ads from the Facebook ad library. So these are ads where the advertiser said that they contain a political message. And then for non-political ads, we took the data set that we collected with our tool, and we asked 3 PhD students to review 10,000 random ads and exclude any politically related ads. Yeah, so we had over 9,000 ads labeled as non-political from the ad analyst data set. So using this data, we trained several models. We went from simple naive Bayes to convolution neural networks. We used word embeddings with Word2Vec and tenfold cross-validation. Nothing extremely fancy, but fair enough. And here you can see the accuracy that the various classifiers had. And also you can see the true positive rate for 1% false positive rate. So what does this 85% true positive rate for a 1% false positive rate means is that out of all the political ads, we were able to detect 85% of them, and we only labeled 1% of the non-political ads as political ads. Yeah, so here when you deal with these unbalanced problems where the number and the fraction of political ads it's much higher than the non-political ads, we really need to be careful with the false positive rate, because you don't want if you have a higher positive rate, you will end up labeling lots of non-political ads as political ads. Yeah. Okay, so this accuracy, it's not too bad. So what we did next is that we try to answer the initial questions, whether the Facebook ad library is missing political ads. So what we did is that we took all unique ads received by the ad analyst users in the electoral period, 38,000, and we apply the convolutional neural network model, and we obtain 835 ads as being labeled as political. So what are these results? We're saying is that 2% of the ads people see on Facebook were political, but were not declared as political by the advertiser. And you need to compare this number with the fraction of official political ads, which during this period was 2 to 4%. Okay, so what we saw during the Brazilian presidential election, that there was kind of half of the political ads, let's say, were declared as being political, but half of the political ads were not declared as political. So if we go back to the initial question of whether the Facebook ad library is missing political ads, we saw that yes, a considerable amount of political ads was missing from this ad library. Okay, so this was the first study that we did. So the next thing that we focused our attention is that we said, okay, we in this work we actually did not bring proof that we can reliably detect political ads. And what I mean by this is that for this first work, we were happy to detect some political ads, but in nowhere we claim that we can collect all the political ads or detect all the political ads. So what we actually did in the first study is that we took a bunch of political ads, yeah, and we we built an algorithm that it's able to detect similar looking political ads, yeah. But we didn't actually ask the question, what is a political ad, and whether the input that we took, it's representative in any way of political ads in general. Yeah, so this was the focus of our second work. So let's start from the beginning then. So first question is, what is a political ad? Okay, and here I put the definition that Facebook has for what is a political ad. So I'm going to read out loud. It's like a political ad. It's made by, on behalf of, or about a candidate for public office, a political figure, a political party. So broadly speaking, are ads from political actors or ads about political actors. Then they have a second line, which is said that there are ads about any election, referendum, ballot initiative, including go out and vote campaigns. So broadly speaking, are ads about election. Elections are on the 5th of July. And finally, we have this category, which is called about social issues in any place the ad is being placed. Yeah. So we call them issue ads, and Facebook, it's giving more what Facebook considers as social issues. You can see here above this definition is civil and social rights, crime, economy, ads about education, and environmental politics, guns, health, and immigration. Okay, so this is the definition provided by Facebook with these three categories of ads: political actors, election, and issue ads. Now, if we look at other platforms, what we see is that there is no clear consensus of what is a political ad and what it is not. And the most important difference is that Facebook and TikTok are considering issue ads as political, while Twitter and Google do not consider issue ads as political. Yeah, this is the biggest difference between the two. Now we could debate whether one definition is better than the other, but it's not the main point here. So let's keep in mind the Facebook definition, because it is also in line with the definition that is proposed in the EU Code of Practice on Disinformation, where they consider both political and issue ads as being sensitive content. So to kind of get a feeling for why detecting political ads might not be straightforward, I will just give you 3 examples of ads that we found in our database, and I will ask you to say whether you consider them they should be labeled as political or not. So I will just read out loud these examples of ads. So first one is: Christians around the world are suffering for their faith, and there is critical need for Bibles to help them stand strong. Help us meet our goal to reach 10,000 persecuted Christians with God's word and training to discipline more believers. So, so would you say that this is a political ad or it's a non-political ad? Follow-up question is: would you label it differently if this ad comes from a priest or from an advocacy group? Yeah. So my expected answer, if we were in the same room, would be like half of the people say that it's political and half that it's not. Another example is: help us force companies to stop the destruction of rainforest caused by the production of palm oil. Greenpeace will see to it that companies keep their promise to use only palm oil that doesn't come at the cost of clearing forest. So again, this is an ad that it's coming from a non-governmental organization. This is an ad that it was targeted at US citizens. Again, do you think that this is a political ad or a non-political ad, given the fact that it's talking about rainforest, which is not, it's not they don't exist in the US. And a final one, just for fun. This is again a real ad that we saw that was saying, if socialism is really so great, why don't socialist professors teach for free? So again, political, non-political. For me, at least, it's not clear. So what we can see from what I can see from these examples is that even if we have a definition, it's quite hard to apply it in practice. Yeah, what is a political ad? Not always straightforward. And again, when you consider ads about political issues, it's not always clear which issues would be treated as political versus non-political. Is the destruction of rainforest a political issue in the US or not? I don't know, and it also might change with the time. Okay, so what we did in this work is that we try to understand. We took this empirical approach, and we try to see what actual users, whether they they agree on what is political and non-political. So in the previous 3 examples, I cherry-picked them to take some ads that are confusing, but the question was, okay, is this the majority of the ads that are so confusing, or it's only a minority of the ads? So for this work, what we did is that we contacted ProPublica and Quartz that had an extension similar to ours, meaning that an extension that is collecting the ads that people are seeing on Facebook. But on top of that, they also asked volunteers to label whether ads are political or not. So what we had is these 55,000 ads that were labeled as political by at least one user or an advertiser, and that each ad had at least 3 labels. Yeah, so we had the ad and we had at least 3 people that labeled them, and one of them said that it is political. Yeah, so this is the data set that we have, and yeah, sorry, so this is the interface of their extension where they can choose whether an ad is political or not. And in this second image, you can see an ad that was declared as political by the advertiser himself. You can see here under the word wildlife fund that it said that it was paid for by WWF, and this is a mark that this is an ad that was declared as political by the advertiser. So do users agree whether ads are political or not? Well, we saw that there is disagreement on more than 50% of the ads, and in this paper you can just see. So here, what we call strong political ads are ads that everyone agree that they are political. Yeah. What we call political ads is that the majority of people thought that they are political, but at least one person said that is non-political. Then we have the marginally political ads, which the majority of the people said that it's non-political, but we do have at least one volunteer that said it is political. And then we have the non-political ads where all the volunteers said that they are non-political, but the advertiser said that they are political. Yeah. So the way it was calculated is like out of all these ads, here you see an agreement, and on the rest, there is a sort of disagreement between users of whether it is political or non-political. We also checked whether there is agreement between users and advertisers. It's just another way to look at the results. So if we take the ads here that are labeled as political by the majority of the users, we see that 4% and 7% are not declared as political by the advertisers. Yeah, so we do see some advertisers that even if they have like clearly political content, they are not labeling it as such. But we also see the reverse, which is they are a lot of ads that were not labeled as very political by users, but they are labeled as political by the advertisers. So yeah, we do see quite a bit of disagreement, and it's not on a few cases, but it's on a majority of the ads there is some sort of disagreement. So our question was like, next was like, what ads do get labeled as political? And again, we were seeing a wide range of ads. First, we have an ice cream company, Ben & Jerry, which is a business that is inciting citizens to vote. Yeah, it's companies doing political advertising. We have an ad from the Center for Reproductive Rights, which is an NGO that is addressing advocacy messages about abortion issues. And we also have the World Food Program, a charity that is addressing a social issue that does not seem to have a precise link to any legislation in the US. So you see that the difficulty comes from also from both from the diversity of advertisers that are trying to send political ads. It's not only politicians, but you see companies and NGOs, and also the political messages that they have that ranges from very ads that can have a direct impact on legislation to ads that don't have anything to do with legislation. So to get a more precise understanding of who is sending these political ads, we investigate what is the category of the advertiser, and here we can see the split for the different categories of political ads. So I just saw the time, so I will try to go a bit faster. So what we can see is that most strong political ads do come from political actors. But if we look at political ads and marginally political ads, the majority of them do come from non-governmental organization and other similar causes and charities. So what is the takeaway of this result is that specific electoral legislation should not regulate only ads from political actors, which is the case for many of the European countries now. What we can see that in the online world, they are actually everyone is sending ads, and no, there are many types of advertisers that are sending ads. So we need to broaden the scope of what is a political ad compared to the legislation. The second thing is that we try to understand the content of these ads, what issues they are addressing, and for this we set up a prolific experiment where we ask users to choose about what social or political issue the ad is talking about. And here are again the results, the split. So if you look at the ads that were declared as political by users, we can see that a large fraction here, they talk about issue ads. Yeah, they talk about issue. They are not about a politician or a political figure, and they are not about election. Yeah, so we see that this 30-40% of these ads are about issue that people considered that they are political. So again, the takeaway is that Google and Twitter, I mean, in the current definition, they don't consider these ads as political, but we do see quite a large fraction of them that appear there. So what we learned from this disagreement is that the problem is with issue ads that are the troublemaker, because on one hand they contain highly political content, so it is important to label them as political, but on the other hand it is hard to distinguish between what what issue ads are highly political and what issue ads just address humanitarian issues, and when should we draw the line between what is political and what is humanitarian. So this would be like the high level takeaway of this work. So going back to the initial question whether we can reliably detect political ads, my current answer is no, because we actually don't agree of what is political and what is non-political. So yeah, we need to work on that. So I will just say that we, based on this work, what we did is that we wrote a statement with civil societies that we submitted to the Digital Services Act, where we asked for these ad libraries to contain all the ads published on the platform, not only the political ads, because Facebook is not doing a good job of detecting political ads. And we have all this gray area of issue ads that might be political or non-political, and we do need access to see all the ads that are running on the platform to build better algorithms or build a better understanding on what is on how to detect political ads. So the good news was that the current Digital Services Act, the current draft does include this provision to ask platforms to make public all the ads on their platform. So to wrap up, what we need to make the political advertising safer now, it's access to data, so we can audit these platforms and these ad campaigns. And there are two ways of doing this: is either to build systems that ask citizens to donate data about what they see online, or use the law to get access to the data that is necessary to audit platforms. And I think this is quite a unique opportunity now in Europe, is to ask people that are writing these laws for data that we actually need to have in order to detect these malicious ad campaigns. And the final thing, like universal, is having ad libraries that contain all the ads is the first step, but we still need to detect reliably political ads, because legislations in different countries have restrictions on these political ads, on the amount spent, on the time when you can send these political ads. So it's still an open issue, and we also need to get a step forward and also identify what ad campaigns are malicious, besides just detecting what campaigns are political. This is it. Here are the few works that I talked about related to this subject. Thank you.
Thank you, Anna. Thanks a lot. Questions, please.
I have one quick question.
Please, Daniel.
Thank you for the great presentation. My question actually has to do with whether the dichotomy political versus not political is at the core of some of the challenges in the first place, both at the human level, but also at the computational level as an extension. Do you think it's the right framing to think of this binary, very complex category?
So what I can tell you from our data is that this binary thing doesn't work, because there is a lot of confusion. Yeah. So I agree that we maybe a different definition or non-binary thing would be more adequate.
Because if I try to connect it with the examples I gave in the earlier talk, it's highly contextual, right? In Switzerland, literally a few weeks ago, there was a vote about banning the use of palm oil. So it was actually very political if that message had been circulating. So I think one of the challenges is so much context is thrown away when the decisions are made about labeling, that I think we miss a lot of the information that by construction could be there, but we as researchers opt to eliminate for different reasons.
Yeah. So context is important, and context also evolves over time. Like COVID was not a political issue 1 year ago, and now it's a very political issue in many countries. So we do have, I think it's, the question is, what is a political ad? It's what we show empirically is that the current definition doesn't work, and it's confusing people now how to come up with a better definition saying instead, oh, is this ad impacting legislation in your country? That's a different way to define what is political or not, but I don't have an answer for what would be a good definition. And I think maybe political scientists and social scientists they have a more informed opinion about where to go. From our perspective, I think from what we can do as computer scientists is maybe try to think of more finer grain labels, not just political versus non-political, but try to see maybe what issue this ad is trying to address that that could help.
Thank you very much.
Thank you. Other questions? If not, since we are late, let's move to the next presentation and then go back during the discussion to Juana's presentation. So thanks again, Juana. The next presentation will be, yes?
No, thank you for...
So the next presentation will be from Roberto Caldelli, who will speak about deepfake detection through sequence-based features.
Hi, Adrian.
Hi, Roberto.
Can you hear me? Can you hear me?
Yes.
Okay. Can you see my screen?
No. If you are trying to present from the same browser, please move the presentation to another one.
I'm trying to share directly from PowerPoint. Can you see it now?
No.
No.
So maybe you have the same problem as your ghost had. Yeah, no, it's good. Okay.
It's okay?
Yep.
Okay. Okay, so I can start. Okay, can you see full screen?
Yes.
Okay, perfect. Okay, so I think I can start. So good morning to everyone. I'm Roberto Caldelli. I'm part of the research group at the University of Florence. Here are our colleagues working on this topic of deepfake. So my presentation will be on deepfake, and in particular, I will give you an insight following what has been presented this morning at the beginning of the workshop by Akis. He gave a very good overview of the problem with very good definitions. And I will give you just some hints on the work that we have done, in particular with concerning the use of sequence-based feature for deepfake detection. And so I'll try to go quite quick because X has done most of the work. So basically, the context is the use of misinformation as use of information for different kind of purposes, for military propaganda, or, for example, for social network and other scenarios like this. And anyway, in misinformation in this case is done by the use of deepfakes. So deepfakes is, let's say, a new threat. It's not quite new. Anyway, it's not new. And deepfakes are basically videos that are generated to the use of artificial intelligence. And what is important is deepfakes can be images, but basically deepfakes are intended as video. So they contain multiple frames, multiple images. So they are very important, very crucial, because they can have an impact on the transferring emotions and impressions. And another important thing that deepfake videos are often correlated with audio that is changes as well. So it is changed as well. So it's a very crucial. And there are different kinds of techniques that can be used to create a deepfake. And what is important is that it is not as it is intended usually is a face swapping, but we can change different parts of the video. We can change the speech, as I said before, but we can change also some attributes to change the expression. Here you have a quite interesting example of the Italian former prime minister that has been changed quite easily. And the other important thing, I think that it's important to underline that there are different easy to use techniques. Also, smartphone app can be used to do deepfakes in good quality and quite easily. And this is an example. And for example, I put this just for fun. This is Robert De Niro in a Taxi Driver, and this Roberto Caldelli. This is me in the same sequence, and you can see that it's not perfect, but not too bad. For this is enough. But the problem is when this kind of video is not used just for fun, but for application like, for example, revenge porn or cyberbullying. You can imagine that this is very crucial. And I think there's also detection techniques to establish if a video is authentic or not are not so important. So they do not solve the problem, because in this case, important that the deepfake videos is shared, is propagated, and it's not so important that if not so good quality. And for example, you can imagine this case for cyberbullying for the teenagers. Anyway, so this is another. So anyway, on the other side of the deepfake creation, there is deepfake detection that is, however, very important. And these techniques for the detection of deepfakes have been developed, and Akis has done a good overview this morning. And what is I would like to underline, and this most of these approaches, the majority of these approaches are frame-based. So they look for something inconsistency in the frame of the video sequence. And here there is a list of, it's not exhaustive, of different kind of approach that some approach look for inconsistency in the spatial domain in the frames, or for some semantic anomalies, like, for example, the different color of the eyes, because this deepfake videos are generating using neural networks, so it can happen that generates during the approximation of the images some inconsistent, like a different color of the eyes. Another example is the absence of the eye blinking, or the presence or not of the biological signals like the heartbeat, and also the presence of some inconsistency in the symmetry of the face, like you can see here with a quite famous example of the two different eye rings. Anyway, all these methods are based on framing. So what we have tried to do and we have worked on is use approach based on the sequence, based on the evolution in time of the video, because we can imagine that video should contain more information. So the idea that we have tried to work on is to develop an approach that could exploit possible dissimilarities in the video temporal structure. There are some examples in literature. In particular, we have worked on the use of optical flow fields that can be extracted from the video sequence. Here there are two papers that have been published, and you can have a look for more in-depth details on our work. And so optical flows permit to extract motion vector that should exploit, I say should exploit, some different correlation in the interframe. So between frames, between a group of frames, so between different frames at different time. So it's not just in the interframe. And the idea is to try to understand this can be used to determine if a video is original or not. So basically, just a few words what is optical flow fields. Optical flow fields are fields of motion vector that can describe the apparent motions of the objects by looking at the changes in the illumination of the pixels that can be determined by the movement. The movement are apparent movement between the observers, or the point of observation, which is the camera, the acquisition camera, and the scene itself. The idea is that movement are determined, the change in the illumination determined by the movement. This is obviously not always the case, because we can have some changes that are due to changes in the illumination, or we can have some, for example, some occlusion. So it's, in this case, it's quite difficult to determine the movement. Anyway, what we can extract is having frames f at time t and a successive frame on time t plus 1, and determine there are different kind of algorithms to determine the upflow. We can determine the movement that has moved, that has moved one pixel from the position xy to the position x delta x and y delta y. And so basically we can get optical flow generates a bidimensional field with a component on the x-axis and on the y-axis. So this information can be used to try to detect deepfake videos. And basically we have resort to the use of CNN-based classifier. We have tested not so many, but we have tested different neural networks, and the idea is to use so the sequence and to take couple of frames. It depends which sampling rate, so, and we can estimate the optical flow. Then we crop this around the face, because the face usually moment deals with the videos where a person in is represented, so there is the phase that is usually the main modification. And so this crop phase I used to train a network that is able to understand if a video sequence is original. And so I would like to give you just some hints, some results that this method based on optical flow, it's usable and it can provide some good results. So we have here, we have tested on different data sets. Here we have a test, I've reported a test on face forensic plus data set, which is quite well known in this scientific sector. And it contains four kinds, of different deepfake forgeries, which are face-to-face, deepfake, phase swap, and neural texture. And in particular, there are 3 different kinds of compression. So it's C0, it's no compression, and C23 is middle compression, and C40 is high compression. So you can see that the results are quite good for all 4 manipulations, and the accuracy decreases with respect to the different compression rate as expected. So results are quite good, I would say, but at the moment it doesn't seem to achieve the state-of-the-art performance, which are a bit higher with respect to this. So there is some room to work, and so we are working on this. But an important thing that I would like to highlight is if we have tested this kind of approach in a more challenging scenario, which is the cross forgery scenario. Also, Akis this morning talked on this problem, because all the methods that we have, they perform quite well when the model is tested on a kind of deepfake forgery, and it is trained and tested on the same kind of deepfake forgery. But they perform not so well when they are tested, they are trained on a model, on a data set, on a forgery and tested on another one. If you look to, for example, to this figure, I hope you can see my mouse. Here we have that model have been trained on deepfake forgery, which is one of the four forgery in face forensic plus dataset, and with a compression rate of 40. So you can see that when the model is tested on the same kind of forgery, we have a very high performances. Here we have on the blue bar, we have a method that is based, it's a reference-based benchmark, which is based on frame-based method. I don't remember exactly, I think it's based on exception net. And here we have the red one, which is optical flow. You can see the green one, I will talk you this later. So you can see that there is a gap, okay? As I told you before, that we have to try to improve the method. But what's interesting is if we look in a cross-forgery scenario, so the model is trained on fake and tested on face-to-face, face swap, and error texture, we have that the red bar is always higher than the other one, okay, than the blue one in particular. So this seems to me, I would say, that this kind of approach provides a more generalization, which is one of the open issues that also as highlighted this morning. So it seems that this kind of method is able to try to detect the fake also when a specific kind of forgery has not been seen during the training phase. Anyway, when the trained phase and the test phase are matched, the frame-based method seems to be better. The green bar is another important aspect. We are trying to mix the two methods, and so we can see that the results are consistent with the frame-based method. It seems to, let's say, a bit improved when we use also optical flow. This case P is the case of original. P stands for pristin. Okay, so these are results for the original videos, and you can see that this is coherent for all the other kinds of modification. For example, if we take the model trained on neural texture and we check and we look for the test on neural texture, we can see that there is a very big gap from the frame-based and the optical flows. But we can see again that when we are in the cross-forgery scenario, there is a good improvement for the red bar. So you can understand that the method seems to provide a sort of generalization, sort of robustness, I would say, with respect to the cross-forgery scenario. I think it's a good result to work on. So just in conclusion, so you can see that the sequence-based approach can provide some further information to determine, I would say, some specific distortion that are being generated, that are being embedded in the deepfake video during the deepfake video creation. And also, we can say that the optical flow seems to better generalize and perform in challenging contexts like the cross-forgery scenario. So I think it would be interesting to understand if the optical flow extraction and usage optical flow can be improved, or the use of other method that takes into account on of the sequence of the temporal evolution of the frame of the video could help. And there is also a drawback, as usual, that optical flow is quite computationally complex. So the extraction of optical flow is not so easy, and this is a point where we have to work on. I think it's all from my side, and thank you very much.
Thank you, Roberto. Questions? So I have one. Did you try to combine this optical flow with other solutions? So
Yes, as I've shown here, take the slide. We want just this kind of combination. So we have tried to mix here. Okay, the green bar means that we have tried to train our network by using information coming from the frame-based approach, which is the blue one, and with the optical flow. As you can see that we can get an improvement with respect to the blue one, also in the cross forgery. You can see that here there is an improvement in the green. It's very slight. Anyway, it's something. And it seems that the combination it's sort of it's a composing combination. So it seems that optical flow seems to add something that is different with respect to the frame base. Anyway, not so much. It seems that it's not so much.
Thank you. Other questions? Ioannis? Okay. I think Ioannis has a question.
Has a question by phone. But it's not falling. It's not falling to.
No, wait.
I'm sorry. It's just this moment that my son is on an excursion, and this very moment, because he was missing, I called them. Then they called me back to say everything is fine. So I'm sorry about that. I had to take that call.
No worries.
No. It's important.
Basically, I was wondering about the following. These kind of these deepfakes in general, they are trained in an adversarial manner. So these attempts that you're making now here to detect those deepfakes, aren't they actually? So first of all, are there methodologies that using this kind of the detector, let's say, in order to train better the deepfakes? And something that comes from that is there a natural limit now, or are we trying to, these approaches, are they not trying to do a game in which they are basically improving the deep fakes? And isn't there a limit in trying to detect deep fakes by looking only at the content itself?
Yeah, you're right. So if I understood well, you mean that if the creation of the fake is improving, there will be no distortion, no inconsistency in to look at. Maybe it will be this. I think that maybe there is, according to my experience, there are always some traces, some clues that you can look at. Anyway, the other things that I have in my mind that I think is important to investigate, it should be in the what has been embedded in the video sequence at the moment of the generation of the creation, because at the end a deepfake is an MP4, let's say MP4 videos. So there is an encoding phase. So the deepfake creator takes a video and use the technique, the better technique he wants, and at the end there is a coding phase. So, and the coder is standard, so it's not modified, it's not fake. Okay, so I think that my idea is to try to understand if there is something that that is different and remains during the post-coding phase. So when there is the generation. I mean that maybe it would be interesting to look at the motion vectors that are encoded. When we use optical flow, we take the sequence and we try to extract running an algorithm, or it depends on which technique you want to use. And we look at the sequence, we look at the content, and we extract the optical flow. But looking at the content, I would like according to what you have suggested, I think that we can look something that there are some distortions that are embedded, but are embedded in the coding phase. So it means that the coder, when the coder has performed the coding of this video, maybe is looking at deep fake video, deep fake frames, deep fake sequence, does something that is different with respect to what it should have done in an original case. This could be I don't know if this answer to your question, to your suggestion, but I think that maybe there is some information in that direction, and this is not only the content.
Yes, I was thinking a little bit. I'm not sure that I have an answer to that, but it is interesting to look into the generation of the sequence information that can be embedded, that can authenticate the videos, things like this, perhaps. Not that I mean, this is interesting work what you did. Absolutely.
Yeah. It could be something to put together. So look at the content, look also to this, and maybe to other data. It could be interesting.
Thank you.
Okay.
You're welcome.
Thank you. So we're quite late now. Let's move to the final presentation. So thank you, Roberto. So the final one will be given by Serena. Thank you. By Serena Villata from University Côte d'Azur, and it will be about argument mining and political propaganda detection in political debates. So Serena.
Thanks, Andre. So can you see my slides?
Yes.
Okay. So okay, that should be good. Okay, so thanks a lot. This is a joint work with also Elena Cabra, who unfortunately cannot join us today. So our work is on argument mining mainly, so I will present you some results on that. And then also what we are currently doing for detecting propaganda in text online. So what are political debates? Political debates are what we concentrate on for this argument mining. It is, let's say, an opportunity. It provides an opportunity to politicians, but also sometimes to citizens, to exchange opinions about what are considered the most controversial topics of a political campaign. So what was missing some years ago was really an empirical investigation of the kind of arguments we can find in political debates. And so what we addressed actually argument mining, or better, argumentative component identification and classification in political debates. And actually, we also detect what are the relations between the different arguments. So this is a kind of basic step we need to address before then moving towards, let's say, kind of more interesting tasks, more challenging tasks like fallacies detection or fact-checking or the generation of counter-argumentation to fight, for instance, online hate speech or disinformation online. So what is argument mining? Just very quickly, argument mining is a task in computational linguistics where we aim at analyzing text from the argumentative point of view in order to, in a way, identify and classify argument components and relations. The idea is that we can extract automatically this information from pure text, so from unstructured data, and then we can use this kind of structured information we extract from text in order to use argument-based reasoning techniques to make inferences, for instance, generalizations, to know what are the acceptable arguments, to know what are the defeated arguments, and so on. So just to be precise, argument mining is not opinion mining. Sometimes they are confused, but actually in opinion mining, we are interested in knowing what is the opinion of users, for instance, about a certain product. In argument mining, we are mainly interested in knowing why the user has a certain opinion on a certain product. So in general, the pipeline let's say we put in place starts from the unstructured data, so the text, where we detect the argumentative sentences. We classify the different argumentative components we can find in these sentences, and then we predict the structure of the arguments, meaning the relations between the different components we have detected. So that at the end, what we have is a kind of graph like the one which is visualized in the slide, where we know which claim attacks which other claim, and what are the premises supporting or attacking certain claims. And so we can really motivate our reasoning through arguments. So working on presidential debates, it was an interesting use case for us, because actually all the presidential debates between the candidates in the US, so starting from 1916 to 2016, are available online, all the transcripts. So we actually have taken all these transcripts and we have manually annotated them to build what is a gold standard. So we highlighted about 29,000 argument components, which for the majority are claims, which could be expected because in political debates, politicians mainly put forward claim. And there are also quite a lot of premises or evidence that support or attack this claim. So for this manual annotation, we used, let's say, the work of three expert annotators to write the guidelines and to kind of make the inter-annotator agreement, and also other annotators which were non-expert that carried out further the annotation task. Obviously, we computed the inter-annotator agreement for all the different annotators who participated in the annotation tasks. So we have annotated in total 41 debates. So these are the debates we annotated. And here you have the candidates that participated in the debate, the number of tokens, the number of sentences, and the number of words for each of these debates. And as you can see, these debates are quite long. Okay, so it's not just a short discussion. It's really the TV debate, such that the journalist asks a question, then both candidates replies, then sometimes they rebut to each other about their, let's say, their replies, and then after discussing a while a certain topic, then the journalists move on the next topic, and so on. So one debate covers different topics, and it allows the participants, the candidates, to extensively put forward their arguments. So here there is some examples. They are just really some arguments we pick from the dataset. So for instance, we have the argument from Nixon. I believe the programs that Senator Kennedy advocates will have a tendency to stifle those creative energies. I believe, in other words, that his program would lead to the stagnation of the motive power that we need in this country to get progress. So these are two claims for us. And then we have, for instance, again, a Nixon argument down. We have, for instance, two premises, like I favor the president depletion allowance. This is the claim. And then I favor it not because I want to make a lot of oil men rich, but because I want to make America rich. So these are, in a way, the two evidence that are in support of the claim I favor the president depletion allowance. So this is the kind of data we have to deal with. Sometimes it's debates were in a way easier to annotate, even for human annotators. So really the human upper bound was quite high because the difficulty is huge. Sometimes these debates are quite complex. So, for instance, this kind of data is more complex to be annotated than data from, I don't know, from social networks, for instance. So sometimes these arguments are much more complicated. So here there are other examples, but I will not go through all these details. So what we did is that basically we addressed two tasks. The first one is the argumentative sentences detection, which was task 1. And then the argumentative components identification, meaning the classification. So first, we wanted to detect those sentences that we can classify as being argumentative, and then we discard those that are not argumentative, and from those that are argumentative, we then again binary classify them as being evidence or claim. So this is how we split the trained validation and the test set. Anyway, the data set was quite huge, so we had the mean to split it into the 3 standard sets for the experimental evaluation. And concerning features, well, kind of standard features, the part of speech, then we have all the let's say syntactic features, but also the discourse connectives, name entities, and also sentiment, which played quite a role in identifying these components. So these are the results we obtained with a kind of standard machine learning methods, because we use LSTM and different networks. So it's we obtained quite good results given the difficulty of the task, and also with respect to in general to the baselines in argument mining. Same for the second task, which of course this was done in a pipeline. So we in a way accumulate the errors that we did already in the first binary classification, for then classifying also the argument components into claim and premise. But these were the results. So just to go a bit more into the details of what was wrong also in our automated classification of argument components, where there are some misclassified non-argumentative sentences. Sometimes are very short sentences which contain, for instance, an argument indicator such as so. Like for instance, so what should we do? This is classified as argumentative, while really it's not really having some content, so it should be mostly non-argumentative. And then we have also sometimes some claim indicator, then it's used by the candidate in a non-argumentative manner, and sometimes so we misclassified, we say, okay, this is a claim, whilst it was not the case. And then also candidates make final remarks, phrasing their speech like in sentences like this one. I think when you make that decision, it might be, well, if you would ask yourself, are you better off than you were 4 years ago? So this is a kind of sentence that is hard for us to classify. And then, of course, there are also some kind of misclassifications between premise and claims, due to the fact that this component classification depends also on the structure of the arguments that anyway has been annotated and analyzed afterwards. So there is a demo, which is the DeepFusion demo. I will not go into the detail because we are already quite late. So you can check it, the DeepFusion, if you look for DeepFusion on the web, you can find it. It's an online demo, so you can really analyze all these debates and you can visualize the data set in a kind of a user-friendly manner, such that you have the premise and claims highlighted in the text. So what are we working on now? We're always working on this data set because actually we want to build on it because it required quite a lot of time to build it and to annotate it and so on. So our goal now is to detect propaganda sentences in these political debates we collected. So let's take, for instance, this sentence by Nixon. I would remind Senator Kennedy of the past 50 years. I would ask him to name one Republican president who led this nation into war. There were 3 Democratic presidents who led into war, and so on. So this is a kind of fallacy that we can call the correlation thus causation, meaning that there is a kind of correlation between the fact that there was war and there was a Democratic president, but it's not the cause. That's not why the reason why the US were beginning the war. So this is a kind of a, let's say, intelligent way of making the audience think that actually it was due to Democrats each time to run into a war. So that's one of the possibilities. Then we have Trump, which is always a good example. So for instance, if you look at Bill Clinton, far worse, minor words, and his was action. He was what he's done to women. Okay, so he was obviously referring to the Monica Lewinsky effect. So then this is a personal attack fallacy, what we called ad hominem, meaning that he's not dealing with, let's say, the political ideas of Clinton or the political results, or nothing referring to that, but it's really a personal attack. And then we can have also other kinds of, let's say, of propaganda elements that are, let's say, a bit also more difficult to detect, like the one from Kerry. He said, don't take away my hope, because my hope is what keeps me going. And then there is the whole discussion, and you can read it. And this is an appeal to emotion fallacy, which is called argumentum ad passiones. So also the fact of appealing to emotions in the audience. It could be positive emotions, like in this case, or negative emotions, so trying to raise fear, for instance, in the audience, or worries. It's a way to make the audience closer to the candidate, to the person who is delivering the speech, and so making it more open to adopt also the ideas that are put forward. So what we are doing now is the automatic detection of these kind of propaganda elements in the data set. We are, of course, doing a manual annotation first. So we are reading in this work now. These are the kind of categories, the kind of propaganda classes we start with. So the appeal to authority, the ad hominem, the appeal to emotion, the false cause, the argument by repetition, the slogans that are used quite a lot, like it could be "Make America Great Again" or others, and then slippery slope. So these are what we are doing, and then the tasks we want to address on our datasets is the 2 standard propaganda detection tasks put forward, for instance, in the Semeval task or the NLP4AF task. So binary classification, propaganda, no propaganda, and then multi-class classification, so which technique is used in this precise text snippet. So this is done in collaboration with Shore Adadan in the University of Luxembourg, Elena Cabrio here at UCA, and Vorakit always at UCA. And thanks for your attention.
Thank you, Serena. Questions, please? So did you? I have one. Did you try to apply this to to these techniques to, let's say, political text which go beyond debates?
No.
No, because
no. For the moment, we tried. For this, you mean propaganda? Or
I mean,
argument mining?
Argument mining.
Argument mining has been, well, we worked on Twitter, for instance. So we worked on the tweets on the Grexit and Brexit. So there were quite political, not really debates, but tweets. Mm-hmm. And their results are, well, quite good. It's in a way less challenging because it was when tweets were still limited in length. Yeah. So mm-hmm. it was in a way easier to analyze these kind of arguments.
Okay. And what about propaganda?
Propaganda, no. We worked on the data, the two data sets of NLP4AF and the SEMEVAL. So there are no debates, no political debates. There are some political arguments put forward in news, for instance, and so on. So there it works pretty well, our approach, but we still want to test it on these quite challenging data set of propaganda debates.
Okay. Okay, thanks a lot. Other questions? If not, so there was some room for discussion, which is very important. I know, Yanis, how much time should we take, given that we are late for the discussion?
It's up to us.
Okay.
As long as people are available, it is indeed important, and we can spend some time for discussion, conclusions, and so on.
Okay, then let's have an ultra marathon style workshop. See who is the last one to leave. Okay, so we've seen quite a lot of topics. Some of them are like overviews. Some of them are specific ones. Maybe what would be interesting is to see how this fits into the more global context of AI4Media. So mainly what can we use from work package 3 to 5, and how can we feed what work package 6 does into use cases. And with respect to external speakers, what can we take from their works and integrate into the use cases of AI4Media? And now, who would like to start? So everyone is too tired at the end.
Yes, I think matching the developments and the expertise to the use cases in a more detailed and in a more specific way, it's for sure a useful direction, and it's a bit specific because we have already something from the use case side, and now algorithms and approaches seem to be developing in the work package. So, of course, this is a good direction. And maybe for some more, let's say, open issues or aspects, like, for example, the local news aspect, which was presented by Danielle, there can be more specific discussions about people who are interested, and see whether AI4Media and the work package can make some contribution in this field, especially if it seems that it's not covered very well. So there might be room for some novel contribution there. And this was just an example. Maybe there can be new, other new topics like this one.
Mm-hmm. So one other topic which was not discussed today is so we discussed a lot about fake news, mostly from the video side. In the future, I think it would be very interesting to have the people from Fraunhofer telling us about the audio side, and also to advance quite a lot on the text side, because that's also very important. So in terms of how fake messages can be conveyed to users. So are there other questions, remarks?
I guess people are looking forward to the weekend.
Yes, and to lunch maybe for those of us who didn't eat. Okay. So then, thanks again. Thanks to the external speakers, so Juana and Elena. Thanks to the speakers from AI4Media, and thanks to all participants. So we'll try to gather all the presentations and to make them available for later discussion and collaboration, hopefully. So thank you all for participating for today.